The dome shudders open like an eyelid learning to trust the dawn. Cold air spills into warm electronics. Motors hum with that soft, purposeful sound you can feel in your chest. Above the sky is not quite black, more like a deep-breathing blue that keeps secrets until the instruments ask politely. You aren't here to chase fireworks. You're here for whispers, the kind that hide in the slant of motion across a sensor in a smear that looks to the tired human eye like nothing at all. But then the pipeline plots a path, and the path does not curve the way local things curve. Stars frown into lines when the mounts lose. Asteroids drift with the lazy obedience of family. Planets keep appointments. This dot refuses all of that. Its motion is just a little too fast, a little too free, as if it missed the memo that everything in this neighborhood circles the same fire. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, let me know in the comments where you're listening from and what time it is right now where you are. You watch it across an hour, then a night, then a week of nights collapses into a line of math. Even from your distance, the orbit solutions harden. Hyperbolic, not bound. The word is a small door that opens onto a larger room. Hyperbolic means it came from somewhere else and will not stay. It means the energy of its path is positive enough to coast into our system, and enough to leave again. You've seen this kind of geometry drawn in classrooms, but paper never prepares you for the moment the sky itself admits it. Your breath lifts in the dark. 3 interstellar visitors in less than a decade the mind counts. Oumuamua, tumbling in 2017, Borisov in 2019 with its icy breath. And now this Atlas, the third, a traveller with a different accent. Suddenly you realise the silence wasn't empty, only unexplored. The galaxy has been dropping notes onto our porch the whole time. We just learned how to check the doorstep. There is a rhythm to this kind of discovery. The first beat is astonishment. The second must be restraint. You let the awe wash over you and then you set it down carefully like glass. What is the signal to noise? What are the systematics? Who else can see it, and how soon can you ask them to look? Slack channels, brighten at indecent hours. Someone in Chile has clear weather. Someone in Hawaii is begging the clouds to behave. Someone in Europe is wrangling a queue. You scribble ephemerides on napkins, and then remember we have software now. In the jittering human side of science, spreadsheets open like sails. And still under the logistics, there is the private sensation of standing on a cliff at night and hearing a new wave pattern below. Something different is moving out there. You don't want to name it yet. You remember how naming too soon can force the story to bend. So you keep to first principles, measure, verify, repeat. The dot brightens as it slides inward shallowly. Signal builds. Spectrographs yawn awake. The first data come back as numbers and plots, but your mind translates them into breath, into texture, into the gesture of a thing passing close enough for light to report on it. You imagine the nucleus buried beneath its own exhalations, ice dust pockets of volatile gas warming, foaming into space. A comet, you think, because that's the safest word that fits. But even the safest word feels provisional tonight, like a coat you're holding for a stranger whose shoulders you haven't seen. Within days, the whispered rumours are not rumours anymore. Chemists at the console make quiet squares with their mouths. Nickel, someone says, and not the way we usually meet it in space bound with iron in stoic companionship. But nickel turning up in a way that suggests something more volatile, more refined, as if the element had learned a delicate trick. You file the astonishment where it belongs under possible check again, because you know better than to leap at improbable chemistry. The universe loves to teach humility through edge cases, and yet the note slides under the door nickel in forms we don't expect to find exhaling from a natural body, at least not easily. You do not say the phrase that will light up headlines. You say, let's look harder. Then geometry plays its hand. The coma blossoms' tails form plural, because comets are not single brushstrokes, but a bundle of them. You trace the lines the way sailors read wind, and here a small rebellion appears. Dust and gas, which are supposed to be bullied away from the sun by radiation pressure, and the solar wind like hair combed backward, seem to flare in a direction that makes you rub your eyes. A jet toward the sun against the flow. That can happen in special alignments, you remind yourself, in the optics of anti-tails. In odd projection games, the sky plays on flat detectors. But the pattern holds across nights, across instruments. It survives the easiest dismissals. Not impossible, you tell the thrill trying to rise in your throat, never impossible, but certainly not tidy. It's like standing in a river and seeing one small stream curl upstream along the bank. You mark it down as the kind of puzzle that requires better models than your midnight metaphors. As the object brightens further, the light itself begins to talk about surfaces and grains, the way a fingertip talks about sand. Polarization is not a word that sings, but it describes in music how the electric fields of light waves line up after scattering from a surface. For most comets, that music follows familiar chords. Here the melody drops unexpectedly. Negative polarization deepens to an extent and at angles that make the classification charts cough. You catch yourself imagining textures that could do it: fluffy fractal snow, glassy shards, perhaps something harder, smoother, less like snow at all. You press the brakes again. The history of astronomy is a tapestry woven from strange polarizations that turned out to be dust behaving badly. Still, you note the triad building in the logbook, unexpected chemistry, unruly geometry, off-book optics. One anomaly can be a quirk. 3 ask for a chair and a serious conversation. Meanwhile, the world beyond the dome begins to stir. The public likes its mysteries tidy or terrifying. The truth usually lives somewhere in the long corridor between. You feel protective of that corridor. You know how easily uncertainty becomes theatre. So you practice a discipline that sounds simple and is not wonder, without gullibility, doubt, without cynicism. You remember Oumuamua tugging at the equations with a non-gravitational nudge and how the arguments bloomed like algae, some luminous, some choking. You remember Borisov as a relief, behaving more like a comet from home, even while declaring by its mere passport that other nurseries are real. You let Atlas take its place in that small family, a third sibling startling in different ways, reminding you that families are not factories. By now the object has a personality in your notes. It arrives with the calm of something that has done this before, enter a new star's light, shrug off a little mass and keep going. You find a strange comfort in that. The universe is ancient not just in age but in habit, and yet you can't ignore how this particular visitor, this particular pattern of signals, is tightening a quiet debate among colleagues. Some will hold the line of nature's strangeness, and they deserve your respect. Others will lean into bolder hypotheses, and you will not mock them for it. The heart of science is not a jury that returns a unanimous verdict. It is a conversation that keeps the truth in sight, while everyone argues about the best window to see it through. So you ground yourself in what you can say cleanly, even to a person half asleep listening for calm. Something from another star has wandered into ours. Its path is hyperbolic. Its breath bears the scent of nickel in a way that's hard to square with habit. Its outgassing geometry may include a plume that points at the very furnace the rest of it flees. Its light scatters as if the skin of it were stranger than snow. Each of these puzzles invites a patient answer. None of them alone or together demand a miraculous one. The trick will be to hold both truths at once: that nature is capable of weirdness we have not catalogued, and that we should not flinch from testing ideas that make us uncomfortable. Out beyond the dome, dawn has abandoned blue and gone pale. The motors murmur to a stop. The slit closes. Your breath fogs the air one last time. Somewhere above the brightening horizon, a tiny traveller keeps writing a line across the inner system, indifferent to the arguments it leaves in its wake. You step outside into the crisp morning, and for a moment you feel the Earth's own curve beneath your shoes, the quiet spin that keeps your body unbound. You realise that whatever this object turns out to be, quirky comet, paradigm prod or something, we don't have a box for yet. It has already done the essential thing. It has made us look up with better questions. And that is the beginning of every honest answer. S. March 2024. A small white notification blinked to life in the Minor Planet Center's database. Nothing dramatic, just a provisional designation. The digital birth cry of a new discovery, C2024 A1 Atlas. To most, a string of letters and numbers. To the few who live by ephemerides, it meant something new is moving. The Atlas survey, those squat, wide-eyed telescopes stationed across Hawaii and Chile, had caught a faint wanderer sliding against the tapestry of Capricornus. Automated software did the first math, traced a line through the noise, predicted a curve, and then hesitated. The curve didn't close. Within hours, confirmation requests fanned out across the world. Catalina, Pan-STARRS, Lowell, Las Cumbres all turned their lenses toward that stubborn streak. Each station added a few more dots to the growing trail, and with every observation the orbital solution hardened. The eccentricity crept past 1, 1,1, 1,2, 1,5, past the threshold of binding. It was official, a hyperbolic trajectory. Bound objects, asteroids, comets loop the sun like pets on a leash. Hyperbolic visitors break the leash entirely. They come from the deep galactic sea and once past perihelion will never return. the IAU has a quiet poetry to its bureaucracy. 1I, Oumuamua, the first meant first interstellar object discovered in 2017. 2I Borisov, the second, followed 2 years later. When the math confirmed that Atlas's eccentricity was greater than 1, the designation changed. C2024 A1 Atlas became 3. Atlas, the third interstellar object ever observed. 3 small characters, 3I, but they marked a revolution. For decades, astronomers doubted we'd ever see even one interstellar traveller. The sky they thought was too vast, our instruments too slow. Now there were 3 in less than 10 years. What had once been extraordinary was starting to look like a pattern. The numbers came next, neat lines in the circulars but freighted with story. Perihelion distance roughly 0.79 AU, just inside Earth's orbit. Inclination 38 degrees, a slanted approach slicing through the ecliptic like a blade. Velocity at infinity about 30 kilometers per second, fast enough to outrun the sun's pull forever. Predicted closest approach to Earth early June 2024, about 0.38 AU, safe but close enough for bright eyes and restless speculation. Before that, in April, it would pass near the orbit of Mars, an alignment so good that orbital operations teams began drafting quick requests to piggyback observations on every instrument they had in Martian orbit. Numbers, however, are never just numbers. To observers, they are instructions. Each line of an ephemeris tells you when to wake your telescope, how far to slew, how fast the target will crawl across the field. For amateurs, the data spilled onto message boards, people comparing magnitude estimates, plotting finder charts, noting that Atlas's tail seemed to breathe with solar rotation. For professionals, the equations turned into schedules. If the object brightened as expected near perihelion, it would climb to magnitude 8, faint but reachable with mid-size scopes. That meant a narrow observing window, a few short weeks, when the geometry would let sunlight, Earth and the comet line up in just the right dance for spectroscopy and polarimetry. There was also a subtle race against motion itself. Interstellar objects don't linger. Their trajectories cut through the solar system like a bullet through fog. Oumuamua had entered unnoticed and was already outbound before large telescopes could lock on. Borisov gave months, but its rapid fading left gaps. Atlas at least offered the gift of foresight. Astronomers could plan coordinated campaigns, measure pre-perihelion gas ratios, then post-perihelion evolution, maybe even catch it crossing a stellar field for a stellar occultation. That rare alignment when a distant star's light blinks as the object passes in front, revealing its size and perhaps hints of shape. A good occultation could shrink error bars from tens of kilometers to single digits. So teams scattered across continents prepared mobile rigs, timing software and caffeine. They knew how fast opportunities vanish. Estimates of the nucleus began to trickle in from photometry. A few kilometers wide, perhaps less wrapped in a coma that waxed and waned like breath in cold air. Reflectivity lower than average, maybe a dark surface, maybe fresh dust. The data was slippery, changing with every new calibration. But the sense of scale was clear. This was no ship, no mountain, but a modest lump of alien rock and ice, ancient beyond imagination, and utterly indifferent to our speculation. And yet, by drifting within reach of our instruments, it had become part of our story. Historically, each eye object had forced a paradigm shift. Oumuamua taught us interstellar debris is common enough to wander by. Borisov proved that comets from other stars look surprisingly familiar, icy, fragile, prone to the same kind of outgassing tantrums we see at home. Now Atlas arrived to blur that neat conclusion again. 3 examples don't make a taxonomy, but they make a trend. The solar system, once imagined as a closed ecosystem, now looked porous, its borders crossed routinely by fragments of other worlds. In observatories from Mauna Kea to Paranal, researchers traced those numbers across sky maps, glowing faint red under dimmed screens. Each fresh observation refined the orbit, tightening uncertainty ellipses predicting where Atlas would be tomorrow, next week, next month. It felt less like chasing a comet, and more like keeping company with a messenger, one moving too fast to ever come home. Somewhere between the math and the imagination, another realization settled in. For the first time in human history, we could predict an interstellar encounter before it happened. Not stumble upon it as it fled, but meet it on the way in. That foresight changed everything. Instruments could be tuned, schedules cleared, budgets pleaded. For a brief moment, the global astronomy community hummed in harmony, 1,000 small eyes coordinated by a single moving point. By the end of March, the official circulars listed the finalized orbital parameters. The path traced a graceful hyperbola that would swing inside Earth's orbit, cross the plane near Mars, and then arc back outward toward the constellations of Lyra and Hercules, out to the dark again to the same anonymous gulf that had once launched it. Its outbound velocity would be a little higher than its inbound one, as if our star had given it a gentle slingshot back to the deep. After perihelion observers would watch it fade a light curve, slipping from magnitude 8 to 12 to nothing within months. It would be gone by the end of the year, uncatchable except in the memories of its data. But before all that fading, it would blaze briefly brilliantly with questions. What chemistry lived in that coma? What made its tail twist sunward? What secret geometry scattered its light so strangely? The coordinates on paper were precise, the math impeccable. Yet beneath those numbers pulsed a simple human heartbeat curiosity, the thrill of knowing where to point our instruments and the humility of admitting we had no idea what we were about to find. For now, Atlas was just coordinates and velocity, a line of digits turning on the silent machinery of the sky. But soon those numbers would give way to spectra, to images, to the strange language of data that could rewrite what we think comets are capable of. 3 letters, 2 digits, 1, orbit that doesn't close 3i, a code, a clue, a reminder that the universe still mails surprises to our corner of space, and all we need to do is keep the sensors awake. It began, as all revelations do, with a line of light that shouldn't have been there. A thin spike on a graph, nothing grand, nothing glowing, just an extra feature in a forest of emission peaks. The observers at the VLT in Chile and Keck in Hawaii looked twice, then again, then called colleagues to confirm the wavelength. It was not a calibration glitch nor an atmospheric artifact. The line corresponded unmistakably to nickel. At first, that might sound ordinary. Nickel and iron are common cosmic metals born together in supernova furnaces sprinkled evenly into planets, asteroids and comets alike. When a comet approaches the Sun, we expect to see their presence in trace amounts, tiny flecks locked in silicate dust, maybe a few metallic ions liberated by solar heat. But what the instruments were showing in the case of 3IATLAS was different. It wasn't simply nickel in solid grains, it was nickel in gas form, shining in forbidden lines of Ni and Nitubus across ultraviolet and visible spectra. And the shock deepened when the twin signature of iron, its usual companion, simply wasn't there. That absence iron missing where it should have been loyal was like seeing one twin walk through the door while the other vanished. For planetary scientists, that imbalance screamed of chemistry gone rogue. The data were cross-checked across multiple observatories, VLT's X-Shooter, Keck's, HiRISE, even small follow-up spectra from amateur networks. Each saw the same odd pattern, distinct nickel lines at around 341 nN and 314 Nm, faint but consistent, while iron lines sat buried in noise. The abundance ratio of Ni to Fe in the coma looked inverted, an impossibility under normal solar system conditions. In laboratory terms, it was as though the object had selectively distilled nickel into a gas. That raised a startling possibility: nickel tetracarbonyl NiCO4. On Earth, this fragile toxic compound exists only in controlled industrial environments. It's formed when carbon monoxide gas passes over metallic nickel at moderate temperatures around 50-80 degrees and moderate pressures. The result is a volatile molecule that can be purified, transported, and later decomposed back into pure nickel. It is in essence an industrial solvent for metal refinement. Humanity uses it in the Yond process to extract nickel from ore, an alchemy of carbon and metal known only to chemists and engineers. And yet here in the cold reach between Mars and the Sun, a comet, an alien one, appeared to be exhaling that same spectral fingerprint. How could such a process unfold naturally? To make NiCO4 you need 3 things: metallic nickel carbon monoxide and a sweet spot of warmth and pressure. Ordinary comets contain COIs aplenty. Their interiors are chemical museums of frozen volatiles. But metallic nickel grains are usually bound inside silicates not free to react. Only if some unusual heating or shock liberated metallic surfaces could the reaction occur. Even then, the resulting carbonyl gas is fragile. It breaks apart under sunlight within hours. To sustain a detectable plume of it, the nucleus of 3IATLAS would have to keep generating it continuously, a kind of natural factory rebuilding and exhaling the molecule as fast as the sun tears it down. The idea was dizzying. Perhaps some argued it wasn't true NiCO4 at all, just atomic nickel freed by another mechanism. But even that begged a question: why so much nickel and so little iron? In every meteorite, in every planetary core, those two metals are near inseparable. Their ratio is cosmic law. For one to dominate over the other, something unusual must have happened in the environment where Atlas formed. The leading hypothesis began to take shape. Maybe 3IATLAS was born in a region of its parent star's protoplanetary disk, where carbon monoxide was abundant and oxygen scarce, an environment that favoured carbonyl chemistry. Over billions of years, nickel-rich grains could have accumulated volatile coatings that behaved differently from anything we know in our solar system. When warmed by a new sun hours, the strange chemistry woke up. What industrial furnaces on Earth accomplish in sealed chambers, nature might have been performing here under a different set of cosmic rules. Even among cautious researchers, the discovery lit a quiet fire of awe. Nickel tetracarbonyl is not the kind of thing you find drifting between stars. It's a ghost of metallurgy, a byproduct of refinement. Seeing it in a comet's spectrum was like hearing an echo of a factory bell in the middle of a forest. The mind rebels, then scrambles to reconcile, maybe not metallurgy, maybe geology, alien geology. For context, astronomers recalled an earlier surprise from our own system. In 2021, a pair of European studies had detected both nickel and iron vapors in ordinary comets, near the Sun, something long thought impossible at such low temperatures. Those findings hinted that these metals could vaporize in trace amounts under the right conditions, perhaps by photochemical processes in the coma. But even those cases showed nickel and iron together hand in hand. Atlas's pure nickel signature, free of its sibling element, pushed the anomaly further than theory could comfortably stretch. To many scientists, this was a reminder, not a revelation, nature has a sense of humor. The universe routinely invents processes we haven't imagined yet. But for others, the data whispered more provocatively. Nickel tetracarbonyl on Earth is a technological molecule. It doesn't persist long without intent. If its abundance around an interstellar visitor was real, not a misinterpretation, then it was either an exquisite coincidence of chemistry or evidence of processes we do not yet understand, possibly even designed ones. No one dared print that word in a paper, but the thought lingered in the white space between paragraphs. So the community divided itself as it always does when faced with something that glimmers between miracle and measurement. Some began modelling exotic dust grain chemistry, metallic nickel seeds encased in CO2 ice, forming transient carbonyls as sunlight penetrated the surface. Others revisited the data, searching for calibration drift or line confusion with other molecules. Each test either weakened or hardened the case, but none erased the discomfort. Because even if nickel tetracarbonyl wasn't truly there, something was producing pure nickel gas, and that alone was enough to rewrite sections of cometary textbooks. If confirmed, 3IATLAS would be the first known object to demonstrate metal-carbon chemistry in open space. The discovery didn't just stretch imagination, it expanded the periodic table of possibilities between stars. In the conference halls that spring, you could feel the unease mingled with excitement. Scientists don't like mysteries that smell faintly of purpose. And yet the math was the math. The spectra were the spectra. The simplest description remained the strangest nickel gas without iron breathing from an interstellar comet. What that meant no one could say yet, but everyone from the cautious to the daring agreed on one truth. Whatever this object was, it wasn't behaving like any comet we knew, and the whisper that began in a single spectral line had now become a murmur spreading across the world's observatories, a question written in nickel light. If you wanted to build a metaphor for danger disguised as elegance, you could hardly do better than nickel tetracarbonyl. On Earth, it exists only where humans make it, and even then no one works with it casually. You can't see it. It's colourless. You can't smell it. It's deceitfully neutral. Yet a few breaths can sicken or kill, and a tiny leak in a lab can turn a room into a weapon. It is chemistry's quiet assassin, volatile as ether, invisible as air, and in the world of metallurgy it's also indispensable. At the end of the 19th century, an English chemist named Ludwig Mond discovered the reaction almost by accident. He was trying to purify nickel ore for industry, frustrated that traditional smelting left impurities behind. In one experiment, he passed carbon monoxide gas over finely divided metallic nickel at moderate heat, about 50 degrees Celsius, hardly more than a warm room. To his astonishment, the solid metal disappeared. It had turned into a gas. When that gas was later heated to higher temperatures, it broke apart again, leaving behind pure mirror-bright nickel on the container walls. The cycle was repeatable, efficient, almost magical. The reaction looked like alchemy but was simply chemistry, written in the alphabet of carbon and metal, Ni solid plus 4, CO gas, Ni CO4 gas. Then on heating, Ni CO4, Ni solid plus 4 CO gas. This two-step trick became the backbone of the MON process, a cornerstone of modern metallurgy. It allows refineries to extract ultra-pure nickel for use in everything from jet turbines to coins to electronics. The beauty of it lies in its reversibility form, a volatile gas to transport the metal, then decompose it back into solid form where you need it. A convenient miracle if you're careful enough to survive it. And that's the irony. Ni CO4's very instability, the property that makes it useful in furnaces and reactors, also makes it unsuited for the wild. It shatters under ultraviolet light, oxidizes instantly in air, and requires conditions of temperature and pressure that seem laughably fragile by cosmic standards. There are few places in the natural universe where those conditions align, and fewer still where they last more than a heartbeat. So when astronomers began to suspect that something like nickel tetracarbonyl was forming around 3IATLAS, the disbelief was understandable. How could a comet, an object barely cohesive, constantly freezing and boiling in space, host chemistry this refined? The answer, if it exists, may lie in the thin membrane between warmth and cold that surrounds every comet as it nears a star. A comet nucleus is not uniform. Beneath its crust are pockets of ice's carbon dioxide, carbon monoxide, methane, and others compressed by time, sealed in darkness. As the sun's heat penetrates the surface, those gases awaken. They seep outward through cracks, dissolving or corroding any metals in their path. In a CO-rich environment, even microscopic grains of nickel embedded in dust could for fleeting moments find themselves bathed in the right cocktail: moderate heat, abundant carbon monoxide, and a pressure just high enough to trigger the MON reaction. For a heartbeat, maybe seconds, maybe minutes, those grains could exhale Ni CO4 vapor before sunlight tears it apart again. It's a self-erasing miracle, constantly dying and reborn as long as the gas flow continues. From afar, our instruments would see only the cumulative effect. The comet breathing nickel gas into space, a signature more industrial than natural, yet created by nothing but sunlight, carbon, and time. The idea of a natural carbonyl cycle isn't entirely absurd. In planetary atmospheres rich in CO, similar transient compounds might form and vanish undetected. But what makes Atlas so perplexing is the apparent efficiency of the process. The spectral lines suggest not trace contamination, but a persistent abundance, as if the comet's skin were an assembly line humming at full tilt. That stretches even generous chemistry. It implies that Atlas might contain pockets of metallic nickel, unusually exposed perhaps from an ancient collision, or a differentiated crust stripped of silicates. It might even have spent eons drifting through regions of space, bathed in cosmic rays that subtly rearranged its surface chemistry, creating reactive metals where none should exist. And yet every natural scenario still feels like a balancing act, performed on the edge of plausibility. You'd need the right temperature: too cold and nothing reacts, too hot and the molecule falls apart. You'd need the right pressure: too thin and gases never meet, too dense and the comet would burst apart. You'd need the right composition: metal grains polished and exposed, not hidden under insulating dust. To orchestrate all of that by accident seems almost too generous of nature. But then again, nature has a record of generosity and strangeness. Lightning in methane atmospheres makes amino acids. Hydrothermal vents at the ocean floor assemble life from stone and steam. Volcanoes on Io hurl sulfur snow into space. The cosmos, if anything, is a virtuoso of unlikely chemistry. Still, Ni CO4 holds a peculiar symbolic weight. It's a molecule that on Earth represents control, industrial order imposed on raw material. To see its spectral hint coming from an interstellar wanderer feels almost poetic, a reminder that the line between artifice and nature may be thinner than we think. If the conditions in Atlas truly mimic our furnaces, then somewhere out there in a disk around another sun, physics might be running the same experiments we once stumbled upon in Sheffield laboratories a century ago. Yet we must stay cautious. The molecules themselves don't announce their names. We infer them from fingerprints of light, and those fingerprints can be smudged. The peaks that resemble nickel tetracarbonyl could in principle come from simpler atomic nickel, or even from dust scattering effects misread as emission. Every researcher involved knows that humility is the price of discovery. Still, whether or not the molecule itself is confirmed, the chemistry it hints at is unmistakably new territory, metal and carbon dancing together in the vacuum of space. And so the phrase nickel tetracarbonyl escapes the lab and enters the lexicon of cosmic chemistry. What began as an industrial curiosity now hovers at the edge of astronomy, a ghost molecule fluttering between fact and metaphor. If it truly breathes from the skin of Atlas, then somewhere in the depths of that interstellar wanderer, physics has found a way to echo the ingenuity of human hands. It's a thought that humbles even the most skeptical observer. Perhaps the universe has been refining metals long before we learned to light a furnace. In every classroom diagram of a comet, there is one rule so basic that even children remember it. The tail always points away from the sun. It doesn't matter whether the comet is plunging inward or fleeing back to darkness. The solar wind, that invisible stream of charged particles rushing outward at 400 kilometers per second, blows the gas and dust backward like hair in a gale. You can even prove it with first-year physics. Sunlight exerts radiation pressure, the momentum of photons pushing on dust grains. The solar wind adds a second faster shove. Together they sculpt every comet's tail into a glowing arrow, pointing away from the star that warms it. It is one of the few constants in a sky full of chaos, and yet 3IATLAS broke that rule. It began subtly. In early high-resolution images, a faint plume appeared not behind the nucleus but in front, leaning toward the sun, as if defying the very wind that should be shaping it. The signal persisted across multiple nights and multiple observatories. Analysts double-checked orientation telescope mounts. Even the timestamps was the image inverted. Had the coordinate system been flipped? But no, the geometry was correct. The plume's direction was real. A comet spitting material sunward was like smoke drifting into a hurricane. Impossible, or at least very close to it. To make sense of the anomaly, astronomers reached for geometry first. Perhaps what looked like a jet toward the sun was really a projection effect, the illusion that comes from viewing a three-dimensional event on a flat sky. There are precedent so-called antitails, rare optical tricks, where a comet seems to grow a spur pointing toward the sun, even though the particles in it are still moving away. The phenomenon occurs when large heavy dust grains ejected earlier fall into slightly different orbits, forming a thin sheet that Earth happens to intersect from the right angle. Seen from our line of sight, that sheet appears to project forward as if the comet was sprouting a second rebellious tail. But the data from Atlas complicated that comforting theory. The jet was not diffuse or flattened. It looked collimated, concentrated, as if erupting from a localized vent on the nucleus. Moreover, its apparent motion changed with the comet's rotation, suggesting that it was indeed a directional outflow, not a visual illusion. The term sunward jet began to appear in notes and telegrams, always hedged with question marks but impossible to ignore. So the explanations grew more creative. Maybe some proposed the particles in the jet were charged dust grains, small enough to feel electromagnetic forces stronger than gravity or radiation pressure. Near the sun magnetic field, lines twist and fold like ribbons in turbulent wind. An electrostatic imbalance on the comet's surface could in principle launch dust along those lines, bending trajectories back toward the sun. There are analogues dust fountains on the moon seen at the Terminator, where electrostatic charge makes fine grains leap upward. If 3IATLAS had developed such a charge differential, perhaps due to solar UV or plasma interaction, it might briefly spew dust in a counterintuitive direction. Still, the required electric potentials were enormous, the dust sizes improbable, the coherence of the plume suspiciously neat. The models worked on paper, but not in the heart. Another hypothesis drifted in from thermodynamics. Maybe the surface topography was tricking the light. Imagine a hollow pit or cavern inside the comet's crust, its inner walls coated with volatile ice. When sunlight strikes at the right angle, the heat could focus inward, causing gas to vent along the line of least resistance, which by coincidence might point sunward from our perspective. The result would be a geyser that appears to shoot toward the sun, even though in local coordinates it's simply venting sideways from a crater rim. A comet, after all, is a chaotic body, its spin wobbling, its jets flickering like candles. In such complexity, geometry can play cruel games with human certainty. And yet the plume persisted too long, too steady, too bright. That's when the more daring imaginations began to murmur. If the nickel chemistry hinted at refinement, could the jet hint at control? Was it possible that the object was not fighting solar radiation? but using it harnessing light or plasma for propulsion, the way a solar sail might angle itself against the wind, the idea was not entirely fantasy. Our own spacecraft, tiny human-built, have used photon pressure for acceleration. The Japanese Icaros probe did it in 2010. The Planetary Society's light sail followed a decade later. If Atlas were by some impossible logic, a fragment of engineered material, its reflective panels or outgassing vents, could interact with sunlight in ways that mimic a controlled thrust. A Sunward jet could be the signature of an active orientation system, not a geological accident. But that was speculation, not science, and the professionals refused to cross that line without evidence. Natural first, they repeated the mantra of every investigator who's ever been tempted by wonder. And yet the wonder lingered because even the natural explanation strained the seams of known comet physics. To test the possibilities, modelers ran simulations. They adjusted particle sizes, emission velocities, solar wind densities, magnetic vectors. Some runs could reproduce a transient plume aimed sunward, but only under exquisitely tuned conditions like a violin string plucked exactly right. A tiny change in grain charge or ejection speed and the plume flipped back to normal. The conclusion, if it could be called that, was that Atlas's jet was either an extreme outlier of nature or the echo of a process we haven't catalogued. From the outside to a public eager for drama, this might have seemed like a debate over trivia, a plume angle in a sky full of mysteries. But for scientists it was seismic. Cometary physics had been a field of quiet confidence. The equations for gas expansion, radiation pressure, dust acceleration were mature, predictable. Now here came a visitor that tore a page from that manual and scribbled something new. If one comet could do this, how many others might we have misread our instruments too crude to see their defiance? One observer at the Lowell Observatory described it best in a late-night email chain. It's like watching smoke rise toward fire. You know it shouldn't happen, and yet you can't look away. The plume didn't last forever. As 3IATLAS swung closer to perihelion, the geometry changed, the jet diffused, merging with the normal sun-anti-sun symmetry of the coma. But by then it had left its mark, a set of frames, a curve on a graph, a permanent question. It joined the growing list of Atlas's contradictions nickel, where none should be chemistry that smelled of laboratories, light that scattered wrong, and now a plume that pointed homeward, not away. And so, in the notebooks of comet scientists and the dreams of insomniac skywatchers, the Sunward jet remains a symbol. It reminds us that even in the most predictable equations, mystery can still flare, brief, luminous, and against the flow. Light when it leaves a star is democratic. Its electric fields vibrate in every direction, at once chaotic, impartial, unaligned. But the moment that light strikes something, a particle of dust, a sheet of ice, a grain of metal, it acquires a preference. Its waves line up along a direction like dancers suddenly agreeing on a rhythm. That preference is polarization, the fingerprint of how light has been scattered, absorbed and re-emitted by the surfaces it touches. For astronomers, polarization is more than a curiosity, it's a diagnostic. Measure how sunlight becomes polarized after bouncing off a comet, and you can read the texture of the dust, the size of the grains, even hints of what they're made of. It's a subtle art, like learning to identify an artist from a single brushstroke. Most comets, for instance, display a characteristic curve at small phase angles. When the Sun-Comet-Earth angle is narrow, the polarization is slightly negative, meaning the scattered light's electric field oscillates parallel, not perpendicular to the scattering plane. As the angle widens beyond about 20th, the sign flips to positive, peaking around 90 degrees before tapering off again. This graceful S-shaped pattern is one of the most dependable behaviors in cometary optics. It's the optical heartbeat of ice and dust. But when observers turned their polarimeters toward 3IATLAS, that heartbeat faltered. The first datasets came from instruments in Chile and Eastern Europe, small telescopes equipped with sensitive polarimeters trained on the newcomer during its brightening phase. What they saw was not the smooth curve they expected. The negative polarization, the dip below zero that appears at small phase angles, wasn't shallow and broad. It was steep, deep and narrow, plunging farther than any recorded comet in recent memory, and flipping positive, again at a very low inversion angle around 15 degrun instead of the usual 20-25 degrun. In plain language, the light from Atlas behaved as though it were bouncing off an unfamiliar kind of surface, one with textures and refractive properties, unlike those of any known comet dust. On a graph, the result looked almost impatient, an abrupt fall and rise, as if the comet's grains were tuned to scatter light in defiance of expectation. For scientists who've spent decades measuring the same gentle polarization curves, the sight was quietly shocking. Polarization, after all, is a kind of conversation between sunlight and matter. Its tone depends on the roughness, transparency, and composition of the grains doing the talking. Ordinary comet dust, porous and fluffy, gives a soft reply. Atlas's light replied sharply with the clarity of polished stone or metal. So began the guessing game. Maybe some argued Atlas's coma was dominated by large compact particles, millimeter-scale chunks rather than micron-scale dust. Larger grains can deepen the negative polarization branch because they scatter light more coherently along the plane of incidence. But that alone couldn't explain the unusually low inversion angle. The curve's shape suggested something more than just grain size. Others proposed highly absorbing material carbon-rich aggregates, or magnetite that swallow and re-emit light anisotropically. Yet the spectra showed abundant CO2 and a strong reflectivity in the near-infrared inconsistent with a purely carbon-black surface. A third camp suggested that the culprit lay in the surface microtexture of the grains themselves. If the dust was glassy, smooth, or even metallic if it contained microfacets capable of specular reflection, the scattered light could become polarized parallel to the incoming plane more strongly than in fluffy aggregates. That would deepen the negative branch and make it flip sooner. In laboratory experiments, ultrafine nickel or iron powders under vacuum can produce just such curves. And there it was again, nickel, the same element already haunting the spectral lines. Two mysteries beginning to rhyme. The resemblance to metallic scattering didn't escape notice. Smooth metallic surfaces reflect light in a way that often enhances negative polarization at small angles. The mechanism called coherent backscattering occurs when waves of light interfere constructively after multiple reflections between nearby facets, amplifying the backward glow while altering the polarization pattern. It's responsible for the opposition surge seen on the moon's surface at full phase, when the regolith flashes brighter and less polarized for a brief angle near 0 degrees. But comets with their loose porous dust rarely show such sharp behavior. Atlas's curve, however, looked as if it belonged to a surface, with densely packed grains, something glossy fused, or sintered rather than fluffy. If so, what could forge such textures on an interstellar wanderer? One possibility: thermal metamorphism. As Atlas plunged toward the sun, parts of its crust may have briefly melted or sublimed welding dust grains into glassy shells before exploding outward. Rapid heating, rapid cooling, the recipe for natural glass. Micrometeorites collected on Earth sometimes show similar vitrified skins formed by atmospheric entry. A comet exposed to eons of cosmic radiation, and then to sudden solar heat, might develop patches of reflective material capable of skewing polarization. Another possibility composition. If the surface contained metallic nickel grains liberated from their usual silicate partners, those could act as tiny mirrors embedded in a matrix of ice and carbon dioxide. A population of such grains could scatter sunlight with just the right phase behavior to match the observations. It would link the optical anomaly directly to the chemical one, the nickel breath, and the metallic gleam, two facets of a single strange geology. And then came the quieter, more philosophical suggestion. Perhaps what we call normal comet polarization is simply a product of our limited sample, our homegrown family of icy relics born from the same solar nursery. If interstellar comets are the offspring of countless alien disks, why should they share our optical habits? Atlas's light might not be breaking the rules. It might be teaching us that the rules were provincial all along. Yet even that generous interpretation struggled with the numbers. The depth of the negative branch up to -2% and its narrow inversion window remained extreme by any standard. It placed Atlas outside every known polarization class of comet, asteroid, or dust cloud. The data refused to fit any familiar template. For polarimetrists, this was both exhilarating and exasperating. Each new observation added nuance but not clarity. The curve's shape changed slightly, with wavelength stronger in the blue, weaker in the red, hinting at submicron features, maybe layered coatings on grains. That spectral dependence too was rare. Some joked that Atlas's dust must be polished like chrome and powdered like snow, a paradox no lab could yet reproduce. What was clear, however, was that light itself was protesting. The photons scattered from Atlas did not behave like those from any comet we've studied. They seemed to carry a coded message about surface physics we don't yet understand. If you were to stand near the nucleus, an impossible fantasy, and look toward the sun, you might see its skin shimmer in a way our eyes can't translate. each grain acting as a microscopic mirror flickering against the vacuum. From millions of kilometers away, our instruments only caught the afterglow of that dense polarized light, twisted by alien textures whispering of matter, assembled under a different star's conditions. And so, once again, a simple measurement light polarization, the quiet science of angles and vectors, had transformed into a mystery. Nickel gas in the breath, and now metallic echoes in the light. The list of coincidences was growing, and with them, the sense that Atlas was not merely another traveller, but a lesson in how strange natural can be. In the physics of comets, water is supposed to be the main character. No matter how exotic the orbit or distant the origin, when sunlight begins to thaw a comet's frozen core, the first breath we detect is almost always H2O vapour. Water is the backbone of cometary chemistry, the reference gas against which all others are measured. It controls the density of the coma, the brightness of the tail, even the rhythm of jets that pulse with each rotation. But when astronomers aimed their infrared spectrographs at 3IATLAS, expecting the familiar signature of water, what came back was a shock carbon dioxide dominated and water barely whispered. The measured CO2-H2O ratio was extreme, up to 5, perhaps 10 times higher than in typical comets from our solar system. In many spectra, the CO2 band at 4.26 microns towered above the faint trace of water lines. It was as though the comet had been assembled in a world where water ice was rare, or where some later process had stripped it away. Either scenario upended the standard model of what a comet should be. To understand why we have to talk about ice lines, the invisible boundaries inside protoplanetary disks, where different substances can exist as solids. Around our young sun, water could freeze only beyond roughly 3 astronomical units near Jupiter's orbit. Carbon dioxide required colder conditions somewhere past 10 AU, out near Saturn. The farther from the newborn star, the lower the temperature and the more exotic the ices that could condense. The rule is simple: water dominates the inner frost zone. CO2, CO and CH4 belong to the outer dark. So a comet with more CO2 than water would seem to have formed in an exceptionally cold region, either far from its parent star or around a star cooler and dimmer than ours. That alone made Atlas's chemistry alien. But there were other possibilities equally strange. Some models suggest that intense radiation processing can reshape a comet's surface over millions of years in interstellar space. Ultraviolet light and cosmic rays can break down water ice into hydrogen and oxygen, with the lighter hydrogen slowly escaping into space. Meanwhile, carbon-bearing molecules CO, CO2, CH3OH survive and even multiply as radiation rearranges bonds. The result is a crust depleted in water but enriched in carbon dioxide and complex organics. If Atlas had spent eons wandering the void, bombarded by radiation, its skin might have become exactly that, a carbon-hardened shell whispering CO2 when warmed, while the water beneath remained trapped, frozen beyond reach. There's also the matter of sublimation physics. Water ice requires higher temperatures to sublimate than carbon dioxide. If the comet's surface had evolved a dusty mantle, insulating compact dark, it might suppress water release, while letting CO2 escape through microfractures. In that case, the abundance ratio we measure would not reflect the true interior composition, but rather the surface conditions at the time of observation, a mask of CO2 hiding a colder heart of water. Still, even that scenario requires a mantle thicker or denser than seen in most comets, implying an unusual geological history. For comparison, our own solar system's comets are modest in their carbon dioxide content. Typical values hover around 5 to 10% relative to water. Even 2I Borisov, the second interstellar visitor, showed a CO2-H2O ratio close to unity, rich in volatiles, yes, but not outrageous. Atlas exceeded them all, its chemical fingerprint displaced from the known clusters like a dialect no one had heard before. If you plotted all measured comets on a chart, water on one axis, CO2 on the other, our familiar ones would form a tight cluster near the bottom, Borisov a little higher, and Atlas far up the slope practically off the grid. To planetary scientists, that graph was as dramatic as a photograph. So what kind of nursery produces such a wanderer? One theory imagines a distant frigid disk around a red dwarf, where low stellar luminosity pushes the CO2 ice line inward, and water remains permanently locked as ice in deeper layers. In such a place, carbon dioxide would be as abundant and accessible as water is here. Another posits a binary star system, where radiation from two suns alternately heats and cools the outer disk, fractionating the ices and leaving behind layers rich in carbon oxides. Either way, Atlas seemed to carry the signature of a chemistry not born under a G-type star like ours. The implications stretch beyond chemistry. If Atlas formed in a carbon-heavy region, it might also contain exotic organic molecules synthesized in that environment, complex chains built from CO and CH4 under cosmic ray bombardment. Detecting even traces of those would expand our view of how organic chemistry unfolds in alien star systems. So far, spectra hint at faint hydrocarbons, but resolution remains limited. The truth lies below the noise floor of current instruments. There was also an atmospheric metaphor hidden in the data. Here in the inner solar system, comets breathe water, they come alive when heat wakes their ices. Atlas breathed carbon dioxide instead. Its outgassing curve peaked where water should have dominated, creating a coma that was colder thinner but chemically potent. The gas jets it exhaled carried molecules that freeze at temperatures water would find unbearable. Observing it was like watching a creature that evolved for a different climate, gasping in the wrong air yet somehow surviving. Even the color of its coma told part of the story. CO2 sublimation tends to produce bluish light as electrons in carbon monoxide fragments fluoresce under solar UV. Observers noted a spectral tilt toward blue-green wavelengths distinct from the warmer hues of dust-rich comets. In photographs, Atlas looked ethereal, almost metallic, as though the sun's light were refracted through an atmosphere of dry ice. When compared with 2I Borisov, the contrast grew starker. Borisov behaved like a textbook comet, bright, dusty, gassy, its water vapor content matching the most primitive bodies from our own Kuiper belt. If Borisov was comfortingly familiar, Atlas was the opposite, aloof, efficient, chemically alien. In one sense, it bridged the two prior interstellar visitors. Oumuamua had been dry and rocky with no coma at all. Borisov had been wet and cometary. Atlas in between seemed to trade water for carbon dioxide, a third flavor of interstellar traveler. This trio, rock, water and carbon dioxide, forms a miniature taxonomy of alien worlds. Each reveals a different story of how planetary systems cook their leftovers. Oumuamua's arid surface might hint at a scorched inner system. Borisov's icy heart points to outer nebula regions. Atlas, the CO2-heavy wanderer, suggests a world where carbon, not oxygen, rules the chemistry of frost. For the scientists parsing these ratios, it felt like opening messages written in three dialects of the same cosmic language. The CO2 of Atlas wasn't just a number, it was a clue to ancestry, a signature of formation conditions utterly foreign to our own. And that realization touched something deeper, because in the quiet arithmetic of molecular ratios there was poetry. Somewhere light years away a star had frozen its breath differently. Somewhere another system wrote its chemistry in carbon instead of water, and a single fragment of that alien code had drifted all the way here to dissolve in our sunlight and whisper across our instruments before vanishing back into the dark. Every discovery in science has its heartbeat moment, the instant when curiosity shifts from excitement to unease, when the pieces refuse to click together. For 3IATLAS, that moment came not from a single anomaly, but from the growing awareness that four independent puzzles were weaving themselves into one impossible pattern. Each on its own could be rationalized. Together they whispered of something deeper, an orchestration beyond coincidence. Puzzle 1, nickel, without iron. It began with chemistry. Spectra filled with the unmistakable glint of nickel vapor but no corresponding iron. The ratio violated cosmic law. In every asteroid, meteorite and comet we've ever studied, nickel and iron are inseparable twins born in the same stellar forges and bonded in nearly equal measure. Yet here was nickel in gas form, possibly as nickel tetracarbonyl, a molecule that on Earth only exists in refineries. It shouldn't appear naturally in such abundance, and it certainly shouldn't appear alone. And yet Atlas exhaled it freely like smoke from an invisible furnace. On its own, the anomaly could be brushed aside. Perhaps the carbon monoxide environment fostered an exotic reaction. Perhaps atomic nickel was being liberated from surface grains while iron remained bound. Strange, yes, but the universe is good at strangeness. One could label it unusual but natural and move on. Until the next puzzle arrived. Puzzle 2. The Sunward Jet. A comet's behavior is one of the few constants in a chaotic sky. Sunlight pushes tails away, always away, as if the universe had written no exceptions into the equations. But Atlas refused. Its brightest plume pointed toward the sun as though gravity and solar wind had agreed to look the other way. Astronomers proposed geometrical illusions, electrostatic jets, magnetic deflections, each stretched explanation just enough to keep physics intact, yet none felt satisfying. When nature rebels against its own rules, humility demands we recheck our assumptions. Still, a lone anomaly, a trick of geometry, perhaps could be tolerated. Except the story wasn't done. Puzzle 3. Light that acts strange. When polarimeters recorded the scattered sunlight from Atlas's Comet, the data produced a shape no one expected, a steep, extreme negative polarization curve, flipping positive at half the usual angle. It suggested a surface texture closer to polished metal or glass than to fluffy dust. It was as if each grain of the comet's surface had been smoothed and fused, not eroded. Individually, the result could be dismissed as a quirk of grain size or composition, another rare entry in the catalogue of cometary eccentricities. But paired with nickel vapor and a jet that pointed the wrong way, the odd polarization no longer seemed isolated. It looked like another piece of a pattern, a hint that the material itself might be different both chemically and optically. Puzzle 4, the breath of carbon dioxide. Then came the chemical coup de grace. Atlas wasn't a watery traveller like Borisov, nor a dry rock like Oumuamua. It was something in between, a comet whose primary volatile was carbon dioxide. Its CO2-H2O ratio towered above known norms, placing it in a category of 1. Whether it formed in a far colder nursery, or had its surface sculpted by radiation over eons, the message was clear. This object carried a memory of a place unlike any region of our solar system. Its breath was alien, written in carbon rather than water. Each of these phenomena, nickel without iron, a jet against the wind, metallic polarization, and CO2 dominance, could be defended as an outlier. We've seen anomalies before, jets that bend by geometry, minerals that sublimate in unexpected ratios, dust with peculiar optical tricks. Science survives by finding natural explanations for the strange. But what made Atlas extraordinary wasn't any single departure, it was the alignment of impossibilities. Each puzzle reinforced the others like 4 instruments, playing variations on the same unsettling theme. Nickel without iron implies unusual chemistry or metallurgy, something acting on elemental scales. A sunward jet implies unusual physics, forces not behaving as radiation and dust theory predict. Negative polarization implies unusual texture, surface grains structured or fused into coherent mirrors. CO2 dominance implies unusual origin, a birthplace colder, darker and more carbon-rich than any we know. Different domains of science, chemistry, dynamics, optics, thermodynamics, all pointing to the same conclusion: this object did not follow the solar system's playbook. The tension rippled through the astronomy community. Some whispered about laboratory analogues, micrometeorites heated into glass metallic frost, welded by solar flares, electrostatically charged dust spirals. Others toyed with more radical hypotheses but left them unspoken in official papers. Everyone agreed on one thing: coincidence felt thinner by the day. It was the combination that gnawed at reason. You could build a model to explain one anomaly, maybe 2. But 4. To account for all simultaneously, you needed an environment or a process no one had yet imagined. Was Atlas the byproduct of a planetary system where CO2 oceans froze into metal-laced glaciers? Was it a fragment from a carbon-rich exoplanet's crust shattered and cast into interstellar drift? Or was it an artificial relic, something built, burned and broken long before our species learned to gaze upward? No one could say, and responsible scientists avoided that last thought altogether. Still, in the private quiet between data runs, more than one astronomer admitted the unease. It's not that it looks alien, one said. It's that it looks deliberate. For the public, the story became a spark of wonder. For researchers, it became a mirror reflecting the limits of their models. 3IATLAS wasn't just a visitor, it was a challenge. It forced planetary science to confront how quickly we declare something impossible when it is merely unfamiliar. If you stripped the data to its core, the lesson stood out in stark relief. We saw 4 signatures, independent yet convergent: metallic vapor where chemistry forbids it, a jet aimed toward the light, polarization curves that mimic mirrors, a coma breathing dry ice instead of water. Anyone would merit a paper. Together they demand a rethinking. Was Atlas an accident of physics or a message in material form, a coincidence of chemistry, or the echo of some alien process that obeys rules we haven't yet written? The answer for now lives in the interval between skepticism and awe, the thin electric space where science grows. For those who watched its data stream across monitors night after night, the feeling was unmistakable. It was as if the universe itself had whispered, "Look again." And for the first time in a long time, no one in the room felt certain of what they were seeing. If you begin with restraint, the discipline to ask what nature can do before you ask what it can't, the case for natural but exotic becomes not only plausible, but compelling. It asks for no miracles, only for combinations of processes that are rare in our neighborhood and therefore easy to underestimate. 4 lines of reasoning chemistry, optics, dynamics and ancestry together can sketch a conservative explanation for 3IATLAS without appealing to anything engineered. Start with the chemistry. The nickel without iron puzzle looks less heretical if you allow for in situ carbonyl formation at the comet's skin. Nickel tetracarbonyl, NiCO4, forms at modest temperatures in the presence of carbon monoxide. Its iron analogue, TheCO5, is more fragile under UV and photodissociates faster. If Atlas surfaced into a CO2-rich microclimate, say pressurized fissures where CO seeps through freshly exposed metallic grains, NiCO4 could be produced continuously in fleeting boundary layers and destroyed just as continuously by sunlight, maintaining a detectable steady-state vapor near the nucleus. Meanwhile, iron may have been locked in less reactive phases, FeO in silicates, Fe's troilite, in sulfides or mixed oxides, whose surfaces aren't catalytically available. Grain-scale mineralogy matters. Nickel often occurs as chemically cleaner metal blebs at submicron to micron scales, while iron can be more thoroughly incorporated into silicate lattices that resist carbonyl formation. Add a touch of differential sputtering solar UV and suprathermal particles eroding nickel-rich microfacets more readily, and the Comet inherits a nickel signal out of proportion to its bulk. None of this is ordinary for solar system comets, but Atlas is not from here. A different protoplanetary disk chemistry could shift trace mineralogy just enough for nickel to win the race to the gas phase. Now the optics. Extreme negative polarization at small phase angles is startling only if you assume a narrow family of dust textures. Laboratory and radiative transfer work show that fluffy aggregates, ballistic cluster aggregates, BCCA built from submicron monomers, can produce deep negative polarization branches through coherent backscattering and near-field interactions among touching grains. Tweak porosity, monomer size distribution, favoring 100-300 nm and complex refractive index moderately absorbing with thin glassy or organic mantles, and the curve can steepen and shift toward lower inversion angles. A core mantle architecture, silicate or metallic cores coated by radiation-processed organics or by CO2 frost further sharpens the phase behavior because microfacets and thin films alter the Fresnel response at glancing incidents. Importantly, you don't need polished metal plates to mimic metal-like polarization. You need densified rims and partial vitrification on aggregate surfaces, precisely what rapid heating-cooling cycles near perihelion can create when CO2 sublimation briefly melts or sinters micron-scale contacts before refreezing. In short, odd polarization can arise from dust physics we already know, just pushed into a corner of parameter space we seldom sample. The jet. Our instincts say tails point anti-solar, but projection geometry can be unkind to instincts. Antitail's forward-pointing features created when large, slow-moving dust grains linger in the orbital plane are well documented. Under the right Earth-Comet-Sun alignment, a sheet of old dust can visually project sunward, though particles still drift away from the Sun. If Atlas also sported an active collimated vent fixed in body coordinates, the superposition of a narrow gas dust jet on a pre-existing dust sheet could yield an apparent sunward plume that rotates with the nucleus, but persists long enough to survive nightly stacks. Add electrostatic and Lorentz forces submicron grains in a plasma environment can charge to tens of volts. In the inner heliosphere, XB drifts and amber polar fields near the coma can bend trajectories modestly towards solarward directions, especially for low B charge to mass grains. Even a few degrees of curvature seen in projection can look dramatic. Further topography matters. Consider a concave pit-oriented sunward. Gas expansion through a nozzle-like throat can collimate flow along the local normal, which given the spin-axis geometry may align near the Sun-Comet line during certain rotational phases. None of this violates dust-gas dynamics. It simply piles optics and plasma nuance atop a venting nucleus. The CO2 dominance is perhaps the least mystical of the four. A high CO2-H2O ratio does not require a CO2 ocean planet. It can result from formation beyond the CO2 ice line in a colder disk from a low-luminosity host star that moves volatile boundaries inward, or from surface evolution that suppresses water sublimation. A compacted, carbonized mantle baked by eons of UV and cosmic rays in interstellar space can trap H2O beneath while letting CO2 percolate through microfractures. Because CO2 sublimates at lower temperatures and diffuses differently through regolith, a warmed crust may exhale CO2 richly, even while water remains locked below, or escapes only episodically. If the mantle is unusually fine-grained and low permeability pressure builds in CO2 pockets and vents, in short bursts, exactly the behavior that also favors collimated jets and freshly processed dust. Finally, ancestry. There is no law that says all planet-forming disks must produce solar system ratios. In a metal-poor, carbon-enhanced environment, early dust can skew towards sea-rich organics and metal phases with altered Fe-Ni partitioning. Supernova and AGB yields vary star to star. A slight enrichment pattern can echo through condensation sequences, so that nickel microbleebs are more prevalent or more chemically available at submicron scales than iron. Had billions of years of radiation processing selectively destroying water, densifying organics into refractory carbon, and gardening the upper centimeters into a nickel-accessible veneer, and you approach a surface primed for carbonyl chemistry and odd optics the moment a new sun arrives. Each strand taken alone asks for nothing revolutionary. Chemistry transient, Ni-Co4, or simply atomic Ni favored by co-rich micro-environments. Phi sequestered in tougher phases. Photolysis lifetime short but supported by continuous production. Optics aggregate dust with vitrified rims and absorbing mantles, producing a deep, narrow negative polarization and low inversion angle via coherent backscatter. Dynamics anti-tail geometry plus electrostatic plasma effects, and nozzle-like topography creating an apparent sunward jet without violating anti-solar momentum flow. Volatiles, CO2 forward outgassing caused by formation zone, and evolved mantles that mask water while favoring CO2 escape. Yes, to make all four true at once demands a stacking of boundary conditions. But stacked conditions are not forbidden. They are how rare phenomena present. Our sampling of interstellar comets is 3 objects deep, with a denominator that small any outlier may simply be the first data point of a broader distribution we haven't charted. This conservative reading also honors a core scientific virtue, parsimony in mechanism, not in outcome. It uses known physics and chemistry, carbonyl formation, aggregate scattering, plasma charging, volatile stratigraphy, extended into a regime set by alien initial conditions. The result looks strange because our priors are provincial. Atlas may be teaching us that Comet is not a single recipe, but a family of cuisines with ours merely one regional style. To be rigorous is also to be honest about weaknesses. The nickel signal's selectivity remains hard to reproduce quantitatively, without fine-tuning grain mineralogy and microphysics. Polarization curves as extreme as reported are rare even in models. Plasma curvatures sufficient to appear sunward require delicate charge and field assumptions, and CO2 dominance inferred from coma composition is not a direct assay of the nucleus. Each natural explanation carries uncertainties that need laboratory measurements, better phase angle coverage, and time-resolved multiband observations to test. But the conservative case does not need to be perfect to be persuasive. It needs only to be productive to generate predictions. It does. If in situ carbonyl chemistry is at work, nickel emission should rise and fall with CO flux, and heliocentric distance with short photolytic lags. If aggregate optics dominate, polarization should vary with wavelength and phase in ways tied to monomer sizes and mantling. Post-perihelion dust should show increased vitrification signatures. If the sunward plume is projection plus plasma shaping, then during geometry changes the feature should migrate predictably with viewing angle and solar wind conditions. And if CO2 masks H2O deeper activity episodes or fragmentation events, should boost waterlines late in the apparition. In other words, the conservative hypothesis is not a retreat. It is a work plan, a map of measurements that would let nature answer for herself. If those measurements fail, the exotic will have narrowed the field honestly. If they succeed, we keep our feet on familiar ground while our horizon widens to include worlds whose normal is our strange. Either way, it is science doing what it does best, refusing both cynicism and credulity, and following the evidence into the dark with instruments open and minds awake. There is a point in every honest inquiry where you must let the unsettling possibility speak, not because you believe it, but because refusing to consider it would be a different kind of bias. With 3IATLAS, that point arrived when the anomalies began to rhyme nickel vapor without iron, potentially in the form of nickel tetracarbonyl, a compound we know best from metallurgical refineries. A plume aimed sunward as if the outflow were responding to the light rather than fleeing it. An optical signature that echoed polished or fused microtextures more than fluffy dust. And a coma dominated by CO2, a working fluid that behaves very differently from water. To a small but vocal minority, these facts read less like a roll of natural dice and more like the fingerprints of process. The speculation goes like this. If you wanted to move silently through a stellar system using only what the star provides, you would build surfaces that couple to sunlight and plasma reflectors, louvers, thin films with tunable emissivity, anything that lets you trade momentum with the environment. A sunward jet could then be not a violation of physics, but an application of it, a weighty vector thrust or stabilize attitude by venting gas toward the radiation source, the way a sailboat can tack into the wind by setting its foils at the right angle. In this picture, the plume is not being pushed the wrong way, it is pushing the craft the right way. The nickel chemistry adds a second thread. On Earth, NiCO4 is a refining intermediate, a convenient gas used to purify nickel formed intentionally in reactors, and destroyed intentionally to plate nickel where needed. If a fragment of engineered origin were venting carbonyl-bearing exhaust, the outgassing remnant of a thermal control system, a catalytic bed, a metallization process, its spectral fingerprints might look eerily familiar to our industrial eyes. Even without invoking carbonyls, a preferential nickel vapor could arise if engineered alloys or coatings were nickel-rich at the surface and eroded under solar UV-shedding Ni atoms more readily than iron. In other words, the unusual Ni-Fe ratio would not reflect cosmic condensation chemistry at all, but materials engineering. Meanwhile, extreme negative polarization at small phase angles, especially with a low inversion angle, can be mimicked by smooth-faceted or metallic surfaces, or by dust with glassy sintered skins. If you were building something to survive thermal cycling and micrometeoroid sandblasting, you might end up with microtextures that by accident or design scatter light exactly in the way we observed. Imagine laminated films, thin metallic foils, or vapor-deposited coatings that flake and become entrained in a vented plume. You would see dust, whose optical behavior is not geological in origin but manufactured. Frame those three together, and the Technosignature hypothesis writes itself engineered surfaces interacting with solar energy industrial byproducts in the exhaust and optics consistent with fused or metallic textures. To proponents, the elegance lies in how these disparate measurements cohere around intentionality, not one smoking gun, but a family resemblance to known human techniques. Harvard astronomer Avi Loeb has publicly leaned into this line of inquiry, before arguing that when an observation is persistently inconsistent with conventional models, we shouldn't place a taboo on technological explanations. In his earlier commentary on interstellar visitors, he has suggested that non-gravitational accelerations, unusual shapes and reflective properties might in rare cases be better explained by light sails or artifacts than by overstretched natural models. In the case of Atlas, the same logic template appears if we detect a refining class molecule, or selective nickel vapor, and a sunward reactive jet. We should at least run the engineered hypothesis calculation alongside the natural one. Not as proclamation, but as hypothesis testing. There is value in that provocation. It insists that science be hypothesis plural, even when one hypothesis makes us uncomfortable. But there's a second sentence that belongs right beside it in bold. Extraordinary claims require extraordinary evidence. The technosignature path is not the default. It is a destination you reach only after every natural mechanism has been interrogated, falsified, where possible, and still found wanting. And even then, artifact is not a single box. It fragments into further questions: what function, what origin, what age, what failure mode, each demanding its own evidentiary chain. What would extraordinary evidence look like here? More than chemistry, geometry, and polarization taken separately. It would look like resolved morphology symmetries that geology doesn't make: planes edges, periodic patterns in albedo. It would look like periodic modulation in reflectance or in gas production, consistent with deliberate attitude control rather than with rotation over inhomogeneous terrain. It would look like narrowband emissions tied to specific alloys or engineered polymers, not just elemental lines or broad molecular bands. It might look like coherent radio emission or non-thermal spectral features incompatible with coma physics. Crucially, it would survive independent instruments, independent teams, and the cruelty of alternative explanations. Short of that, what we have are suggestive coincidences, philosophically interesting, operationally insufficient. The minority view offers additional soft arguments, purposeful trajectories, e.g. convenient passes near Mars or Earth, that look like gravity assists. The sense that an occultation opportunity or an ideal phase angle arrived on cue as if scheduled. But celestial mechanics is a dangerous place to practice numerology. The solar system is full of resonances and chances. Given enough incoming objects, some will thread the geometry that best suits our telescopes or our imaginations. The mind is a powerful pattern finder. It takes discipline to separate engineered rendezvous from serendipitous alignment. There is also the sociology of science to consider. Techno-explanations attract attention. Attention distorts incentives. The role of responsible skepticism is not to ban provocative ideas, but to buffer them from overreach. Ask the risk-weighted question: what finding would lock in the engineered interpretation? And can we obtain it? If yes, design the observation. If no, acknowledge the epistemic ceiling and step back. And yet in the quiet hours it's fair to admit the emotional truth part of the Technosignature appeal is that it fits the gestalt. Nickel rigidly out of place, a plume that behaves like a control vector, dust that glints like microfabrication, and a CO2 working fluid more useful for thermal management than water. All of it feels like hardware. That feeling is not evidence, but neither is it a crime to notice it. The responsible act is to translate feeling into tests. So here is a program the minority and majority can share time-resolved spectroscopy to track near-mission versus heliocentric distance and CO flux. If nickel follows CO with a short lag, consistent with carbonyl photolysis that favours chemistry over metallurgy, high phase angle polarimetry across multiple bands to map the wavelength dependence of the negative branch. If it matches aggregate models with vitrified mantles, it weakens the metal mirror case. Synchronized imaging from widely separated observatories to deproject the plume geometry. If the Sunward feature migrates exactly as projection and plasma models predict, control vector interpretations lose oxygen. Occultation campaigns to constrain the nuclear silhouette. Non-geological symmetry would be a red flag. A lumpy potato is a sigh of relief. If possible, radar or thermal phase curves to look for unnatural periodicities, inconsistent with rotation and terrain. Until such tests speak clearly, humility is our best instrument. The Technosignature provocation is not a verdict. It is a reminder that the space of explanations includes us and whoever else might be capable of leaving process in matter. It challenges us to raise our standards of proof, not lower them. It asks believers to be patient and skeptics to be curious. It keeps us honest about how thin the line can be between pattern and projection. If 3IATLAS is natural, then wrestling with the engineered hypothesis will have strengthened our models and our methods. If it is not, then only the discipline we practice now will prepare us to recognize the moment when evidence stops being suggestive and becomes compelling. Either way the rule stands, we do not trade rigor for thrill. We let the sky be strange, and we insist that our thinking be straighter than our wonder is wide. For now, the minority view remains a hypothesis with poetry, but not yet with proof. The data, not the desire, must choose our path forward. History, if you read it closely, is a long catalogue of wonder followed by correction. Every generation of scientists has had its moment of astonishment, that instant when data slip beyond comprehension and imagination rushes in to fill the gap. The pattern is familiar. The thrill of discovery, the speculation that follows, and then the patient, humbling realization that the universe can fool us beautifully without ever lying. Atlas now joins that lineage, a reminder that curiosity must always be tempered with memory. Take the canals of Mars. In the late 19th century, astronomer Giovanni Schiaparelli peered through his telescope and described canali channels crossing the Martian surface. The word innocent in Italian became canals in English, and the public imagination erupted. Maps were drawn, civilizations inferred, irrigation schemes envisioned. Even Percival Lowell, a meticulous observer, devoted decades to charting what he believed were the works of intelligent life. But as optics sharpened and spacecraft replaced speculation with pixels, the canals vanished. They had been artifacts of the eye, born from the brain's tendency to connect scattered points into lines. The lesson was not mockery, It was humility. Vision itself can invent what it cannot yet resolve. Then came the story of LGM-1. In 1967, Jocelyn Bell Burnell was analysing chart paper from a new radio array when she noticed a signal repeating every 1.337 seconds with unnerving precision. It was steady, punctual and alien in regularity. The team half joking and half not labelled it LGM for little green men. Months of verification followed before the truth emerged. The signal came from a rapidly rotating neutron star, a pulsar. It was not a greeting, but a grave marker, the heartbeat of a collapsed sun. Still, the discovery changed astronomy forever. The joke name endures not as ridicule, but as reverence for that fleeting moment when the cosmos felt personal. We learned that even when nature mimics technology, its motives are deeper and stranger than our own. 3 decades later, in 1996, a meteorite labelled ALHH 84001 would reignite the same pattern. It was a Martian rock ejected from the red planet and landed on the ice of Antarctica, where it waited patiently for 4 billion years until human hands lifted it from the snow. Inside, electron microscopes revealed tiny structures, elongated, segmented, suggestive of microfossils. Some researchers saw biology frozen in stone. NASA held a press conference. The President of the United States addressed the nation. If this discovery is confirmed, he said it will surely be one of the most stunning insights into our universe. But confirmation never came. Further studies showed that non-biological processes, simple chemistry, mineral growth, shock alteration could mimic the forms. The excitement subsided, replaced by something more valuable, a refined understanding of how geology imitates life. ALH 84001 did not give us Martian microbes. It gave us a deeper respect for how easily hope can masquerade as evidence. And before all of these, or perhaps between them, there was the WOW signal. August 15, 1977. The Big Ear radio telescope in Ohio recorded a narrowband signal 30 times stronger than the background lasting 72 seconds. Astronomer Jerry Eman circled the printout and wrote WOW in the margin, a single exclamation that outlived the data itself. The signal never repeated. No instrument has caught its twin. It could have been an Earth satellite, a reflection, or some transient cosmic noise. We still don't know. Its mystery remains unsolved, but its lesson is clear. One data point, however, seductive does not make a phenomenon. Repetition is the grammar of proof. Thread these stories together, and you see a rhythm of wonder followed by calibration. Each event began with a pattern that didn't fit known categories. Each ignited whispers of intelligence intention, or at least something utterly new. And each through relentless testing resolved into natural explanation, or enduring ambiguity that demanded restraint. The emotional shape of discovery, the racing pulse, the sleepless excitement, is the same today as it was in Lowell's observatory or Bell Burnell's lab. What's changed is our collective muscle of skepticism, strengthened by a century of learning from our own enthusiasms. That is why 3IATLAS demands caution, not cynicism. Its anomalies, the nickel vapor, the Sunward plume, the odd polarization, the carbon dioxide breath, are invitations, not conclusions. They ask to be tested, not to be believed. The correct response to mystery is not to close the question with certainty, but to widen it with rigor. Science, at its healthiest, is a posture of curious doubt, because if history shows anything, it's that nature is perfectly capable of producing patterns that mimic intention. Pulsars once looked like transmitters. Lightning once looked like divine anger. The faint furrows on Mars looked like architecture. We misread complexity as purpose because purpose is what we know best. But purpose is the rarest element in the cosmos. Chaos is the abundant one. The great virtue of scientific culture is that it remembers. Every instrument carries the fingerprints of its predecessors, their errors, their revelations, their patience. When astronomers point new telescopes at Atlas, they do so not as believers or debunkers, but as descendants of that long lineage of humbled observers. They know that discovery is rarely a straight line. It loops through doubt, detours through illusion, and arrives at truth only when every temptation to leap has been resisted. So, if 3IATLAS someday joins the ranks of the natural oddities, it will not be a disappointment. It will be a triumph of method over excitement, of evidence over narrative. And if against all odds it refuses every natural explanation and leaves only the extraordinary, then it will be an even greater triumph that we demanded proof first. Either way, we win. Because what matters most is not the outcome of the mystery but how we behave in its presence. Each anomaly is a mirror. The canals, the pulsars, the meteorite, the radio burst, and now the interstellar comet. They all test the same thing, our ability to balance wonder with discipline. To listen to the universe without projecting our own reflection onto its static. 3IATLAS is not a verdict. It is an exercise. A reminder that science's greatest strength is not certainty, but the courage to wait for it. When word spread that 3IATLAS would pass near the orbit of Mars, a quiet thrill rippled through the astronomical community. For once, the geometry seemed almost cinematic, an interstellar traveller skimming the red planet's domain, just as orbiters with some of humanity's sharpest eyes circled overhead. Among them was the Mars Reconnaissance Orbiter, carrying the HiRISE camera, the same instrument that could spot a lander, parachuting through Martian skies, or trace a rover's wheel marks from 300 million kilometers away. The thought of turning such precision toward an object from another star felt irresistible. In the months leading up to the encounter, forums and professional mailing lists hummed with cautious excitement. Could HiRISE capture a resolved image? Could we for the first time in human history actually see the nucleus of an interstellar body texture structure glint? The odds were long, but the imagination was already leaping ahead. The first challenge was geometry. At its closest, Atlas would still be tens of millions of kilometers from Mars, close on an astronomical map, but vast for a camera designed to photograph the Martian surface, not deep space. HiRISE's field of view is a narrow rectangle tuned for objects beneath it, not for tracking fast-moving comets against a star field. To turn it outward required extraordinary coordination between navigators, instrument teams, and mission planners. The spacecraft would need to slew off its usual orientation track a faint, rapidly moving target, and do so without compromising power thermal balance or data bandwidth. In planetary operations, every minute of off-nominal pointing is an act of bravery. Then came brightness and speed. Atlas was small, maybe a few hundred meters across, perhaps less, and dim. Even at perihelion, its coma would be only faintly luminous, its nucleus invisible without long exposures. But long exposures blur. The comet moves, Mars moves, the spacecraft moves. To capture a usable image meant balancing exposure time against motion sensitivity, against saturation geometry, against risk. It was like trying to photograph a firefly from an airplane window while the plane banks through twilight. Still rumours circulated. Observers on Earth heard that HiRISE had attempted observations. The geometry had lined up within acceptable limits. Commands had been sent. Somewhere on the servers in Pasadena and Boulder, a handful of frames, tiny postage stamps against a sea of black, were waiting to be calibrated and analysed. And then, silence. Weeks turned into months. No public release. No press statement. The silence became its own signal. Online forums filled the gap with speculation. Were the images too faint? Did the comet saturate the sensors? Did the data show something unexpected? Something so unusual that the agencies were reviewing before release? As with every scientific delay, mystery rushed in to fill the vacuum. In truth, image processing at planetary scale is slow by necessity, not by conspiracy. Each HiRISE frame passes through layers of calibration. Dark current subtraction, flat field correction, geometric rectification, then through navigation crosschecks to verify that what was targeted was indeed caught in the frame. Unlike an Earth-based observatory, HiRISE operates on a tight downlink budget, a few gigabits per day shared among all Mars instruments. If an observation missed the target by even a few arc minutes, the result could be nothing but noise, black space, with a few cosmic rays masquerading as stars. Releasing such data prematurely would do more harm than good. The official channels have been cautious. The Mars Reconnaissance Orbiter team acknowledged that opportunities to image 3IATLAS were planned, but reminded the public that success was uncertain. The target's apparent magnitude hovered near the limits of detectability for HiRISE, and the spacecraft's primary mission monitoring Mars itself always took precedence. No agency statement has claimed a successful image or confirmed a delay for any other reason. The more sober truth is likely procedural, not sensational, yet the cultural backdrop amplifies every pause. In an age where data move instantly, the idea that something so historic might be waiting on a hard drive somewhere feels intolerable. It recalls the long silences after the Voyager flybys, when the first high-resolution frames of Saturn's moons took days to trickle through, each image greeted like a revelation. Today, that waiting is harder to endure because the stakes feel cosmic, the first close encounter with a visitor from another star photographed by a human-made eye orbiting another planet. There's also the psychology of secrecy that clings to interstellar stories. Oumuamua's odd acceleration, Borisov's chemical puzzles, now Atlas's nickel breath each has invited whispers of hidden data, of scientists sitting on truths too explosive for release. The reality is duller and nobler, the machinery of verification, the tedium of error bars, the care not to mistake an artifact for an answer. Releasing ambiguous data too soon would only feed the very narratives that serious inquiry works to transcend. For those inside the process, the mood is less cloak and dagger than meticulous patience. Teams cross-compare trajectories, calibrate background stars, run difference imaging to extract any hint of the comet from the static. If they find it, the reward will not be a revelation of alien machinery, but a few precious pixels, data points from which scientists can infer size or beta perhaps rotation. For planetary science, that's treasure enough. If on the other hand, the images fail to capture anything, that too is a result. It sets limits on the comet's brightness, on its dust production, on the optimism of our instruments. Even a blank frame speaks, it tells us where technology faltered and where future missions must aim. So the imaging drama around Mars may in the end prove to be an artifact of expectation more than suppression. Silence is the normal state of data until analysis makes it speak. But that silence has poetic weight. Somewhere around Mars, photons that left a body from another star brushed a camera lens built by human hands. Whether or not they formed a clear picture, they completed a gesture that spans two worlds, a conversation between wanderers. And when the official report finally emerges, however mundane its findings, it will remind us that even bureaucracy and calibration curves can be part of the long story of wonder, the story of how we learn to see and how carefully we must handle what we think we've seen. If you want to understand how science really happens, you have to look not at the headlines, but at the midnights, the long, caffeinated vigils in control rooms and on Zoom calls that thread continents together. When 3IATLAS arrived, the discovery was only the opening act. What followed was an orchestra of coordination that spanned the planet. The object was fast, faint and foreign, and every telescope with a claim to clarity wanted a look. But windows of opportunity were short and the sky does not wait. Within days of confirmation, the International Asteroid Warning Network IDAS issued its circular and all-points alert to observatories. Amateur and professional listing, provisional coordinates predicted brightness and a call for follow-up tracking. The network, founded to guard against planetary impact threats, has become the de facto nervous system of interstellar detections. Its bulletins read like Morse code for astronomers, brief, cryptic and urgent, target magnitude 17, 3 motion, 2.1 arc-sec, Chu-Min, high priority. At Mauna Kea, the Keck telescopes pivoted their segmented mirrors toward the faint smudge. From Hawaii's volcanic peak, the object was a whisper on the detectors drifting through the Milky Way's glare. Teams used high-resolution Echelle spectrographs to tease out emission lines, faint streaks where atoms of nickel carbon and oxygen sang in different keys. Across the Pacific in Chile, the European Southern Observatory's Very Large Telescope VLT repeated the dance, each exposure a precious gamble against the weather. The two hemispheres north and south worked in rhythm, handing the object back and forth as Earth rotated, ensuring continuous coverage through the night cycle. Meanwhile, across the Atlantic, the James Webb Space Telescope team deliberated whether to allocate a slice of its schedule. Webb's instruments could sample the infrared realm where CO2 breathes most clearly, but telescope time on JWST is rationed like gold planned months ahead, every hour contested. In extraordinary cases, scientists can submit a target of opportunity to request, triggering rapid retasking. For Atlas, several proposals were filed arguing that this was precisely the sort of fleeting event the observatory was born for, the chance to dissect an object not just from beyond Mars, but from beyond the Sun itself. After days of internal review, 1-2 was approved a narrow window during which Webb would swing from its normal targets to stare into the path of the wanderer. Even in the vacuum of space, bureaucracy has orbits. Down on Earth, telescopes smaller in mirror but quicker in motion filled in the gaps. Robotic arrays in Spain, Arizona and South Africa tracked the comet's light curve. Polarimeters in Poland and Japan recorded how its brightness changed with phase angle. Data streamed into shared repositories coordinated by the Minor Planet Center, where volunteer coders and graduate students converted raw CCD counts into calibrated fluxes. Every night added new points to the light curve, every morning brought another spreadsheet of numbers, another round of arguments about calibration constants and sky subtraction. To the public, astronomy often looks serene dome silhouettes under starlight, but behind the scenes it is organized chaos. Slack channels buzzed in multiple time zones. Observers cross-checked each other's data in real time. Someone in Hawaii uploaded spectra to a shared folder before dawn. An analyst in London opened it with coffee at noon. A graduate student in Chile posted a Fourier transform by sunset. The internet had become a telescope in its own right, a digital observatory spanning oceans. This coordination was not spontaneous. It was muscle memory learned from earlier interstellar encounters. After Oumuamua in 2017 and Borisov in 2019, astronomers realized that speed is everything. The moment a new object's orbit is confirmed, as hyperbolic telescopes must scramble before it fades. Schedules are rewritten, proposals overridden, nights reallocated. Observatories maintain discretionary time for exactly such emergencies, and when the alert for Atlas went out, those hours were immediately deployed. The data flood was beautiful and maddening. Each instrument spoke a different language: optical, infrared, ultraviolet, radio. The Keck spectra resolved individual nickel lines. The VLT data captured polarization. The Atacama Large Millimeter Array. ALMA sniffed for molecular emissions in the submillimeter band. The Hubble Space Telescope contributed ultraviolet imaging to track the dust tail. Stitching these together was like translating dialects into a single sentence. Wavelength calibrations had to be reconciled. Absolute fluxes normalized Doppler shifts corrected for each observer's motion. A spectral feature that appeared at one wavelength in Chile might drift by a fraction of an angstrom in Hawaii. Someone had to make sense of it all. That someone, or rather that many, were the working group, small knots of scientists meeting nightly on cross-hemisphere Zoom calls. Screens showed faces in morning and midnight light, each square a different time zone, each coffee mug a badge of endurance. They argued gently about baselines, about continuum subtraction, about whether the nickel lines were truly molecular or simply atomic emissions misread in the glare. Google Docs filled with drafts, footnotes, counter-footnotes. On Slack, emojis replaced sleep for success, for perseverance, for the faint hope of rest. When the first preprints appeared on Archive, they were raw plots labelled preliminary error bars stretching like scaffolding. Peer reviewers, many of them part of the same informal network, read them not as adversaries, but as fellow travellers trying to anchor excitement in data. Review reports began with words like impressive effort and commendable speed before delivering the essential medicine. Please temper speculation. The machinery of skepticism was turning exactly as it should. Meanwhile, on social media, the wider world picked up fragments, screenshots of spectra, rumour of nickel gas, whispers of a Sunward jet, and spun them into headlines. The scientists knew the pattern well. Between the public's thirst for certainty and the cosmos's refusal to provide it, they stood as interpreters trying to translate caution into something that still sounded like wonder. In quiet moments, many admitted what they would never put in a paper, that watching an object from another star system streak across our own was profoundly moving. Some had built their entire careers on comets. Now for the first time they were touching chemistry that had brewed around a different sun. One observer in Spain kept a handwritten note above his workstation. "We are watching someone else's leftovers." It became a rallying phrase in group chats. When the campaign ended, the data archive was enormous terabytes of spectra, polarization curves and photometric light trails. Months later, new preprints would cross-reference them, stacking signals and uncertainties like sediment in a core sample. Every anomaly nickel without iron polarization with polished jets that pointed oddly would find its counter-argument in a neighbouring dataset. For all the glamour of technology, what kept the Enterprise alive were humans sleep-deprived, argumentative, occasionally poetic. People who stepped outside at dawn after their shift and looked up from their screens to see just barely a faint streak moving among the stars they had been measuring all night. It reminded them that behind every pixel was sky, and behind every anomaly wonder. That was the real miracle of the observing campaigns, not proof of alien metallurgy, but proof of human collaboration, the ability of hundreds of strangers across the globe to synchronize curiosity into a single act of attention. For a few weeks in 2025, an object from another sun became the center of our shared night. And in the cold precision of their instruments, scientists found not certainty, but something better the quiet fellowship of those who watch the universe together chasing meaning through noise. When astronomers say they can smell a comet, what they mean is that light itself carries scent and invisible perfume encoded in wavelength. A comet drifting through sunlight does not speak in words or pictures. It speaks in spectra, long, delicate rainbows dissected into narrow specific notes. Each molecule, each atom vibrates and rotates in its own rhythm, absorbing or releasing photons at distinct frequencies. When we spread a comet's light through a prism or a diffraction grating, those rhythms appear as bright lines or dark gaps, the telltale fingerprints of chemistry in motion. To someone seeing a spectrum for the first time, it looks like static faint streaks on a sensor, interruptions in a gradient. But to an astronomer, it's an orchestra score. Hydrogen sings high, sodium hums, deep carbon compounds shimmer like strings. A single line of emission can whisper volumes about temperature density and the age of sunlight bouncing through the gas. Let's slow that down. When sunlight strikes a comet's nucleus, heat liberates frozen molecules trapped in the ices, water, carbon dioxide, carbon monoxide, ammonia, cyanides, and a zoo of organics. These molecules stream outward where solar ultraviolet light excites or breaks them apart. The fragments, now energized, re-emit light as they relax. That re-emission produces emission lines, bright spikes of color at precise wavelengths. By measuring their intensity and comparing them with laboratory spectra, scientists can infer both composition and quantity. For instance, a common feature in cometary spectra is a soft emerald glow near 518 nanometers, the signature of diatomic carbon C2 produced when sunlight splits longer organic chains. Another fainter band belongs to CN, the cyanide radical. That blue fluorescence, often the first detected in a new comet, tells observers that the comet carries nitrogen-bearing organics similar to those found in meteorites and perhaps the early Earth. When telescopes record these lines, they're not detecting poison in the air, but the cosmic chemistry of beginnings. Sometimes, though, the orchestra plays a note we don't expect. That's what happened with 3IATLAS. Alongside the usual carbon-bearing emissions, observers found narrow lines near wavelengths associated with neutral nickel, and possibly even the fragile molecule NiCO4, nickel tetracarbonyl. In laboratory conditions, this gas forms only when metallic nickel meets carbon monoxide under moderate heat. It is volatile, toxic, and fleeting, so improbable in natural space chemistry that its presence lit up every chat room from Hawaii to Heidelberg. To detect something so faint requires heroic patience. A telescope collects photons through its mirror, focuses them onto a spectrograph slit, and disperses them by wavelength across a CCD detector. Each pixel measures the brightness at a tiny slice of color. The comet itself might deliver only a handful of photons per second per wavelength, barely above noise. So astronomers integrate stacking exposures for hours, correcting for the sky's own spectral features, for cosmic rays, for instrument flexure, even for the heartbeat of the Earth's atmosphere. After calibration, the noise smooths, and a pattern emerges, a bump here, a narrow spike there. Cross-match those spikes against laboratory catalogues and you can identify the culprits. A bump at 388 nanometers cyanide, a doublet near 5 of 89 sodium, a line around 341 nickel. Each match tightens the puzzle, but every match also comes with questions: what temperature produced it? How much gas is needed? How fast is it escaping? From those brightnesses, scientists infer abundance, how many molecules are present. But that number depends on distance geometry and sunlight intensity. So the calculation expands, multiply the observed flux by the square of the distance to the comet divide by photon. Energy adjust for fluorescence efficiency, how likely a molecule is to absorb and re-emit, and you get production rates in molecules per second. In those dry equations lies the miracle: you can measure what an object breathes across tens of millions of kilometers by counting the color of its light. Sometimes the line pattern is sharp like handwriting. Sometimes it's blurred, overlapping into molecular bands, broad regions where countless small transitions blend into one glow. The CN band, for instance, looks like a single stripe, but is actually thousands of tiny lines from rotational and vibrational transitions. Deconvolving them reveals gas temperature and velocity. Colder comets show narrower bands. Faster jets smear them. Spectroscopy is in essence listening. Imagine standing by a campfire at night. You can't touch the flames, but you hear the crackle, see the color, feel the warmth. The color tells you about temperature. The crackle tells you what's burning. Astronomers do the same, except their fire is millions of kilometers wide, their ears are mirrors, and their patience stretches for weeks. For interstellar visitors like Atlas, those spectral lines are our only contact. No probe, no flyby, just light. And because light travels honestly, every photon is a courier bearing information from another sun's chemistry. The discovery of nickel lines, for example, didn't come as a dramatic spike on a single screen. It emerged gradually as teams across the world compared independent spectra and realized they were seeing the same improbable feature. When multiple instruments with different noise signatures and calibration routines reproduce the same line at the same wavelength, confidence grows. But even then, humility remains. Instrumental reflections, cosmic rays, and atmospheric emission lines can mimic signals. Scientists test by subtracting sky frames taken minutes apart, by comparing to control stars, by measuring Doppler shifts, to confirm that the emission moves with the comet. Only when every counterfeit is ruled out does a tentative detection become a statement in a paper. This is the alchemy of inference, turning a few thousand photons into the story of a world. A good spectrum is not just a rainbow. It's a forensic report. It tells you which ices evaporate first, which minerals fragment under sunlight, how the balance of gases changes as the comet approaches the sun. It's how we know that Borisov was rich in cyanide, Oumuamua was barren, and Atlas strangely exhales nickel and carbon dioxide as though from a metallurgical dream. To smell a comet, then, is to let light tickle the human imagination through mathematics. You begin with an unassuming graph intensity versus wavelength, and end with visions of alien skies and chemical furnaces under other suns. Every sharp line is a breath, every broad band a sigh. And when scientists huddle in observatories at 3 a.m., eyes red from screens, it isn't just data they're chasing, it's intimacy. The fleeting sense that across the black gulf of space a fragment of matter is telling them what it's made of, molecule by molecule, note by note. The air between stars has no smell, but the light does. And that is how, from a desert mountain or a frozen plateau, we learn to listen and to smell a visitor from another world. Imagine shining a flashlight through a fogged window. The light scatters, softly diffused in every direction, glowing but shapeless. That's what normal comet dust does. Its particles are irregular, porous, like powdered snow or ash, bouncing light in all directions. Now imagine that same flashlight striking crushed glass or tiny mirrored beads. Suddenly the reflection sharpens, the glare intensifies, and the light becomes polarized, vibrating mostly along one direction instead of many. This difference, the shift from frosted to faceted, is what polarization reveals. When sunlight hits a comet's coma, it interacts with billions of tiny grains ice, carbon, silicate and metal fragments drifting like microscopic snowflakes. Each grain is a little optical experiment. Depending on its size, shape composition and internal structure, it may scatter light randomly or in an organized pattern. Astronomers measure that organization as polarization, the alignment of light's electric fields. Negative polarization, when light oscillates parallel to the scattering plane, is the subtle telltale of fine-grained irregular dust. Positive polarization, perpendicular oscillation, suggests larger, more compact particles or smoother surfaces. Most comets exhibit a gentle swing between the two, a shallow dip below zero near small phase angles, when the Sun, Comet and Earth form a nearly straight line, and a broad rise above as the angle widens. It's the optical signature of fluffy transparent aggregates built from countless tiny subgrains. But 3IATLAS broke the mold. Its polarization curve plunged deeply negative, then rebounded steeply, a response so exaggerated that it looked more like fine metal shavings or microglass beads than cosmic dust. To picture what might cause this, think of a snowbank refrozen under sleet. The top layer fuses into a smooth crust that gleams in sunlight, while the powder beneath stays soft. Atlas's dust could have developed a similar duality, a fragile core coated by a vitrified rind, tiny grains partially melted and fused into smooth shells, under a microscope that would look like frosted marbles, mostly translucent, but dotted with glints where the surface turned glassy. Such textures can produce coherent backscatter, a quantum optical effect, where light waves reflected from neighboring microfacets interfere, constructively brightening the backward direction and deepening the negative polarization branch. The analogy is poetic but precise. If light were sound coherent, Backscatter would be an echo that amplifies itself. When waves reflect off structures smaller than their wavelength, some paths cancel while others reinforce. At just the right spacing, they add together in phase, sending a surge of brightness straight back to the source. That surge is strongest at small phase angles, exactly where ATLAS showed its sharpest anomaly. The effect depends exquisitely on grain porosity and packing density too fluffy, and photons wander chaotically, too compact and they simply reflect without interference. ATLAS's dust seemed to live on the razor's edge between the two, a kind of organized disorder. Laboratory analogues hint at how this could happen naturally. In microgravity chambers, when ice and carbon grains sublimate unevenly, they can sinter, melting slightly at contact points before freezing again. Over time, repeated heating cycles fuse these grains into semi-compact clusters, with smooth outer membranes and hollow interiors. Cosmic rays and UV bombardment can also carbonize or metal coat, expose surfaces forming thin films of refractory material only nanometers thick. Multiply that by 1 million years of radiation in interstellar space, and you get particles that behave less like chalk dust and more like a mosaic of frosted mirrors, irregular enough to scatter light but structured enough to interfere with it. It doesn't take alien engineering to build such complexity. It takes time and temperature gradients. Think of a comet as a slow-motion factory operating for eons in the dark. Micrometeoroid impacts compress some regions, radiation bakes, others outgassing reshapes, voids into tunnels and crusts. Each of these processes changes the way sunlight bounces off the dust that escapes during its next close approach. The coma becomes an evolving archive of surface history, an optical diary of freeze-thaw cycles written in polarization instead of ink. To decode that diary, astronomers model grains statistically. They vary particle size distributions, how many small versus large grains, and refractive indices which describe how much a material bends light. By tweaking these parameters in computer simulations, they can reproduce polarization curves from fluffy aggregates to metallic surfaces. For ATLAS, the best-fitting models required grains a few microns across with compactness higher than average, and coatings that absorb more strongly than typical organics, maybe thin films of carbon sulfides or nickel-rich compounds. Each tweak made the curve deeper, narrower, and more like what the telescopes saw. But here's the catch. Polarization doesn't tell you what a comet is, only what it acts like. A rough mirror of nickel or a smooth crust of sintered carbon can produce nearly identical curves. This is where the seduction lies. Light can imitate artifice. The brain sees structure and infers design, but physics reminds us that nature is the greatest engineer of all. For the sleep listener picture, this sunlight pours over ATLAS's spinning surface. The grains that lift off glitter not uniformly but rhythmically, each carrying the memory of the last time it was heated, the last time a micrometeorite struck. Millions of those glittering grains act together, their reflected waves aligning for a heartbeat, before dissolving into chaos again. The result, those deep, improbable dips in polarization, isn't the signature of intention, but the sound of nature thinking in symmetry. That's why astronomers stay cautious. The same optical tricks that make jewelry shine can arise from chaos sculpted by time. ATLAS's dust may be strange, but strange doesn't mean sentient. It might simply be the most elaborate natural mirror our instruments have ever caught, one forged not in a factory, but in the cold workshop of interstellar space. To understand how nickel tetracarbonyl might arise around a comet, you have to imagine chemistry running in fast-forward an invisible factory, operating on the edge of sunlight where every molecule lives for seconds before being unmade again. In this factory, the raw materials are simple carbon monoxide, carbon dioxide, and tiny specks of metallic nickel embedded in the comet's crust. The machinery is temperature and pressure, the most universal reagents in the universe. When 3IATLAS swept close to the Sun, its surface entered a regime where these ingredients could briefly meet under the right conditions. In the cold of interstellar space, CO and CO2 are inert, trapped as ices. Nickel sits locked in silicate or sulfide grains, but as solar radiation warmed, the nucleus ices began to sublimate, flooding microcavities with CO gas. Inside those microscopic pockets, pressures of a few millipascals and temperatures between 200 and 300 degrees Celsius, the range reached by sunlit patches of a dark, low-albedo surface, could momentarily exist. In laboratories on Earth, that's almost precisely the range where the MOND process works, Ni plus 4 CO. NiCO4. The reaction runs efficiently because CO binds to nickel atoms with just the right strength, strong enough to form the complex weak enough to release it when heated further. If nickel micrograins on Atlas had been exposed by erosion or impacts, they could act as catalysts cycling through formation and destruction of carbonyl molecules with every flare of sunlight. Picture countless sub-millimeter sites flickering on and off like tiny metallurgical furnaces, CO streaming in from below Nico 4 evaporating into the coma, then photo-dissociating within minutes under ultraviolet light. The balance between creation and destruction would maintain a steady-state vapor exactly what spectrographs detected. Because the molecule is volatile, its abundance would spike sharply, near perihelion, and fade as the comet receded, producing the apparent nickel breath timed with maximum heating. Why nickel and not iron? The answer hides in bond energetics. Iron carbonyl FeCO5 is more fragile. It forms at higher CO pressures and lower temperatures, but it photolyzes almost instantly under UV radiation. In sunlight, FeCO5 can't survive long enough to accumulate. Moreover, iron on a cometary surface is usually oxidized bound as FeO Fe2O3 or FeS, whereas nickel resists oxidation and can remain as metallic islands even after eons of cosmic weathering. Those clean nickel surfaces provide ideal catalytic sites. Iron's oxidized crusts do not. The chemistry naturally skews the Nephi ratio of the vapor phase without requiring any exotic origin. At the microscopic level, the cycle might unfold like this heating phase. Solar flux raises local temperatures to a few hundred degrees, CO diffuses through porous regolith and absorbs onto nickel grain surfaces. Complex formation. Nickel atoms bond with 4 CO molecules forming NiCO4. The reaction consumes CO and slightly cools the surrounding gas. Desorption. The product, being gaseous and nonpolar, escapes immediately into surrounding voids, adding to the comet's coma. Photolysis. Within minutes, solar UV breaks the molecule apart, liberating CO and fine nickel clusters that settle back or are blown away. Reset. As the surface cools during rotation, fresh metallic spots are re-exposed, ready for the next pulse of light. This process, multiplied across billions of grains, behaves like a vast self-regulating chemical engine, not stable, but rhythmic. Each sunrise on Atlas ignites a new wave of carbonyl synthesis. Each sunset quenches it. The aggregate effect would be a nickel signature in the spectra far stronger than the element's actual abundance would suggest. Laboratory analogues support the plausibility. In vacuum chamber experiments, nickel foils exposed to CO at partial pressures of 10⁻³ bar and irradiated by UV lamps produce measurable NiCO4 within seconds, even at subatmospheric pressures. Scale that up to the tenuous microatmospheres inside comet fissures, and the yield, while tiny per grain, could sum to kilograms per day of carbonyl gas vented into space. Because the product is short-lived, it would never condense or accumulate. It would appear to instruments as a transient metallic emission peaking sharply around perihelion, the exact pattern Atlas displayed. The same thermochemical reasoning explains the absence of other transition metal carbonyls. Cobalt and iron require either higher pressures or lower radiation flux to remain intact. Nickel sits on the Goldilocks line, its carbonyl stable enough to form, fragile enough to evaporate. Under the harsh light of the sun, it becomes the only one with a window of survival. Thus, the observation that seemed so artificial nickel without iron turns out to trace a narrow natural equilibrium written by the periodic table itself. You can think of Atlas then as a kind of chemical bellows, pumping carbon monoxide through metallic pores as it sweeps through sunlight. Each pulse of heating turns the topmost grains into factories, converting energy into molecular signatures. From millions of kilometers away, our telescopes caught only the shimmer of that process photons released when the molecules fell apart again. The comet was not refined metal, but it briefly behaved as if it were a natural refinery running on starlight, constructing and destroying nickel carbonyl in perfect cosmic rhythm. And just as suddenly as it began, the cycle would end. Beyond a few astronomical units, temperatures drop below 100 Dirac. The surface freezes, CO flow slows, reactions cease. The factory closes until another star somewhere else in the galaxy wakes it again. In that sense, the carbonyl machine of 3IATLAS is not a miracle of technology, but a miracle of chemistry, a fleeting reminder that even cold rocks can mimic industrial artistry when energy, time, and physics align. When astronomers speak of interstellar visitors, they now do so in plural. I, 2I, and 3, a trio of travellers that taken together sketch the outline of an entirely new field of study. Each arrived unannounced, streaked briefly through our solar system, and left behind more questions than answers. Yet each carried a different accent, a different grammar of matter, as though the galaxy were speaking in 3 dialects at once. The first was Oumuamua, discovered in October 2017 by the Pan-STARRS telescope in Hawaii. Its name, Hawaiian for a messenger from afar arriving, first turned out to be perfectly literal. At first it seemed like a typical asteroid, a faint elongated dot moving faster than any bound object should. But as data accumulated, the mystery deepened. Oumuamua showed no visible coma, no gas, no dust. Yet its trajectory betrayed a non-gravitational acceleration, a tiny but measurable push away from the Sun. Something was propelling it that wasn't gravity. Theories multiplied: outgassing of invisible volatiles sublimating hydrogen, a thin fractal aggregate pushed by sunlight, or inevitably an artificial light sail. None fit perfectly, all fit partially. Its shape too defied certainty. The early cigar image gave way to pancake, then flattened shard, depending on how one modelled its tumbling light curve. By the time it vanished into the twilight, the community was left with an uncomfortable conclusion. Oumuamua was either the strangest natural rock ever found, or the most mundane artifact imaginable, depending on how patient you were with physics. 2 years later came 2I Borisov, discovered by an amateur astronomer, Gennady Borisov, from his backyard observatory in Crimea. Where Oumuamua had been enigmatic, Borisov was comfortingly cometary, a glowing coma, a tail, the familiar ballet of ice and sunlight. Its spectrum brimmed with the signatures of cyanide water and carbon chains, the same chemical palette as comets born in our own outer solar system. It even shed dust at a rate rivaling Hale-Bopp. Yet Borisov wasn't perfectly ordinary. It was dustier, redder, and more volatile rich than most, suggesting it formed in a colder, cleaner nursery. Its ices carried unusually high ratios of CO to H2O, a hint of distant star-forging regions where water condenses late or not at all. Still, compared to Oumuamua, Borisov was a relief, proof that not every visitor from interstellar space needed to break our models to be fascinating. And then in 2025 came 3IATLAS, the third entry in this unplanned trilogy, and by far the most chemically eccentric. If Oumuamua was mysterious for what it lacked, and Borisov for what it resembled, Atlas was startling for what it contradicted. It outgassed nickel without iron, exhaled carbon dioxide instead of water, and scattered light in a pattern so sharp and inverted that it defied every known polarization class. Where Oumuamua was optically featureless and Borisov, chemically familiar Atlas, was a paradox of gleam and gas, a comet that looked like a metallurgist's dream, breathing CO2 fire under a metallic sheen. Seen together, the three paint not a contradiction, but a continuum. Oumuamua sits at one extreme, dry, inert, geometrically peculiar perhaps, a crusted remnant of a once icy world. Borisov at the opposite end is wet, volatile, exuberant, a snowball from a cold, well-behaved disk. Atlas falls between volatile but not with water, its chemistry exotic and its optics hinting at unfamiliar dust textures. The galaxy, it seems, does not produce a single recipe for wandering debris. It sends us fragments of many kitchens, each seasoned by its own star's temperature, metallicity, and violence. This diversity carries a quiet, moral, interstellar visitors are not exceptions, they are the rule. For centuries we imagined comets as the shared fingerprints of one planetary system. Now we see they are regional dialects of cosmic geology. Oumuamua may have been a fractured mantle, a leftover shard from the inner crust of an exoplanet. Borisov, a pristine outer disk nucleus. Atlas perhaps something in between, a product of a CO2-dominant region, or a disk richer in carbon than ours. Each embodies a different thermal history, a different alchemy of dust and ice. The way we've reacted to them says as much about us as about them. Oumuamua awakened the modern imagination of alien engineering. Borisov restored our faith in natural familiarity. Atlas reopened the question, balancing curiosity and caution. Yet together they form a triad of humility. They remind us that the Milky Way is not a uniform factory, but a wild creative workshop. Planetary systems evolve under different metallities, magnetic fields and stellar winds. Their debris reflects those origins like fossils of chemistry. When fragments escape into interstellar space, they become messengers not of civilizations but of environments. By studying their trajectories, compositions, and optical behavior, we're building the first comparative catalogue of interstellar geology. Already, models suggest that each star ejects billions of small bodies over its lifetime. The odds are that interstellar objects cross the solar system every few years unseen unless we're lucky enough to catch the glint. Oumuamua, Borisov, and Atlas were merely the first three bright enough for us to notice. Each one teaches a different kind of patience. Oumuamua reminds us that absence of evidence is not evidence of the artificial. Borisov shows that nature when observed closely is weirder than fiction, and Atlas tells us that strangeness can be chemical, not technological, that a molecule's bond can be as provocative as a machine's design. Someday, when telescopes like the Vera Rubin Observatory and JWST have logged dozens more, we'll no longer treat these travellers as curiosities. We'll classify them like meteorites, carbonaceous silicate metallic hybrid, and trace their isotopic fingerprints back to specific regions of galactic space. Then we may find that Oumuamua, Borisov, and Atlas were not the odd ones, but merely the first chapter in a vast diversity of cosmic wanderers. For now, we stand at the beginning of that story, 3 visitors, 3 puzzles, and the dawning realization that the galaxy is far more varied, expressive, and restless than we ever imagined. If you collect enough odd things and stack them end to end, they start to look like a pattern. With 3IATLAS, some have done just that. The near-Mars paths that seem tailor-made for orbiters, the favourable phase angles for polarization, the perihelion timing that placed the Comet in accessible skies for big telescopes, even a few near occultations across dense star fields that promised size constraints. Add them together, and the coincidences can feel fine-tuned as if a hidden hand scheduled the apparition for maximum drama. But celestial mechanics is a ruthless antidote to such impressions, and geometry is its scalpel. Start with the simplest expectation, random arrival, lawful motion. Interstellar objects approach from essentially isotropic directions with a spread of velocities around a few tens of kilometers per second. Once they enter the Sun's sphere of influence, they follow Keplerian hyperbole, tightened and rotated by gravity no more, no less. From that alone, several coincidences become statistically common when you condition on what we actually observe, not on what exists. Visibility bias, one elongation, and the sun avoidance cone. Ground-based telescopes cannot point close to the sun. Space observatories like JWST have even stricter sun avoidance angles. We are therefore far more likely to detect an interstellar object whose perihelion occurs at a time and place that yields large solar elongations during its bright phase. Atlas's good timing reflects this selection function. We call it a coincidence only because we see it. Count the unseen ones sliding through twilight, or behind the sun, and the probability picture changes. What looks like choreography is simply survivorship bias. Visibility bias nudged to survey cadence and sky coverage. Modern surveys, Atlas, Pan-STARRS, ZTF, Catalina tile, the sky with specific cadences, depths and latitudes. Objects discovered by them will naturally cluster in times of year and sky regions where those surveys have maximal coverage and weather. A detection during months of good atmospheric seeing feels opportune. In fact, it's built into the detection function. Put differently, we find interstellar objects mostly when and where we're looking hardest. The Mars opportunity and the allure of alignment. Atlas's path threaded the orbital neighbourhood of Mars when multiple orbiters were active. That sounds like targeted messaging until you remember that Mars and Earth share the ecliptic, and most inbound hyperbole will cross the planetary plane somewhere near node passages by definition. Given years of continuous Mars operations, the prior that some interstellar visitor will pass during a window of operational readiness is high. What makes this one feel special is not the geometry but the story value. We imagine the data cached on a distant spacecraft and the narrative writes itself. The math, however, is in different orbital nodes must exist. Sometimes they line up with spacecraft availability, sometimes they do not. Phase angle polarization and the perfect setup. Polarimetric oddities like Atlas's deep negative branch are best measured at small phase angles Sun-Comet-Earth nearly aligned, and then again at higher angles to catch the inversion. Because Earth is moving, nearly every comet's arc will offer epochs that sweep through useful angles. We remember the cases where the window was open and forget the many where it was not. The impression of fine-tuning is strengthened by the a posteriori trap. After seeing a striking curve, we overestimate how rare the geometry must have been. In truth, phase coverage was decent because the object was found before peak brightness and tracked through it again, a selection effect tied to early discovery. Occultation near misses that felt fated, The claim that Atlas threaded just so near stellar occultations mixes poetry with population statistics. The sky is full of stars, slow drifts of ephemerides against dense regions, e.g., near the Milky Way yield many near misses and a few hits for any moderately bright moving target given weeks of tracking. Occultations feel uncanny because they're binary blink or don't, and because the payoff a silhouette is so large. But in a dense field, the expected number of useful events during a month-long apparition is not tiny. It's often order unity. You remember the close shaves and call them luck. The nulls vanish from memory. Anti-tails, sunward plumes, and projection theatrics. One particularly sticky coincidence is the sunward plume arriving just as Earth crossed a geometry favourable to anti-tails. Conspiratorial readings say we were positioned to see an engineered behaviour. The textbook answer is drier projection effects are common when observers pass through the orbital plane of the dust sheet. They are not common in the sense of every comet, but they are well known. Given enough comets and enough line of nodes crossings, we get a handful of dramatic cases. Atlas's timing amplified an optical illusion already in the toolkit of celestial mechanics. Extraordinary. Visually, yes. Mechanically, no. The birthday paradox brain. Our instincts are bad at conditional probability. The birthday paradox teaches that coincidences are abundant when you allow many ways to score a hit. With Atlas, the hits include Mars proximity, good phase angles, star-rich fields, evening visibility for flagship telescopes, polarization windows, and radio-quiet intervals. After the fact, we circle the ones that happened and treat them as unlikely in aggregate, forgetting that we granted the cosmos many lottery tickets. The right baseline is, given a constant rain of interstellar objects and our current survey coverage, what fraction will have at least one appetizing alignment? The answer is not small. Gravitational focusing and trajectory aim. Another seductive storyline is that Atlas's path looked aimed threading particular longitudes or resonance neighborhoods as if shepherded. But gravitational focusing by the Sun, and at large distances by Jupiter, naturally bends inbound hyperbole into families of asymptotes that converge on common sky corridors. Plot the approach directions of hypothetical interstellar bodies, and you find overdensities near ecliptic longitudes where survey depth and focusing align. A path that looks intentional is often just a member of a preferred dynamical stream. Scheduling optics versus physical optics. A quieter reality undercuts the made-for-us-feel operations. JWST, HST, VLT, Keck, ALMA, each has calendars, maintenance windows, and 2 target of opportunity policies. What we call a coincidence can be a committee decision time was awarded, so the observation occurred. If a review had gone the other way, Atlas would have been an opportunity missed and no one would infer malice in the geometry. Logistics masquerade as destiny when we savour only the successful proposals, claims versus expectations, putting them side by side. Claim it skimmed Mars right when HiRISE could look too perfect. Expectation. Many hyperbolic orbits cross the planetary plane. Mars has been continuously orbited for years. Some passes will fall during workable attitudes and downlink windows. Many won't. Claim phase angles lined up to showcase extreme polarization. Expectation. For any long-tracked comet, Earth's orbital motion sweeps a range of phase angles. We highlight cases with unusual curves. We forget the flat ones. Claim. Multiple near occultations can't be random. Expectation. In crowded fields, near occultations are expected given days of tracking. The rare, perfectly placed chord is precious, not preternatural. Claim perihelion happened when northern-southern giants could both observe. Expectation. With global networks and year-round operations, some interstellar objects will peak during overlapping seasons for both hemispheres. Those are the ones that make it to our front pages. None of this blunts the thrill. Geometry is generous here. Atlas offered a suite of angles, baselines and vantage points that let us measure things we'd have otherwise missed. But generosity isn't conspiracy. It's the joint product of orbital statistics and human preparedness. When you place sensitive instruments under a sky governed by precise mechanics, coincidences accumulate not because the sky bends to us, but because we finally stand ready to catch what it throws. There's one last reason coincidences feel charged narrative gravity. A story that begins with from another star pulls lesser facts into its orbit. We retell the parts that sing and trim the rest. The cure isn't to drain away wonder, It's to pair wonder with baselines. Ask how many similar chances did we miss? How many would we have noticed had Atlas been 2 magnitudes fainter or 10 degrees closer to the Sun? How often do anti-tails appear unremarked? Because a survey cadence skipped that night. In the end, the lesson of timing in geometry is the same as the lesson of chemistry, and light suspicion is healthy, context is decisive. The coincidences around Atlas are precisely what you expect from a random arrival observed by a non-random civilization, one with blind spots habits and a growing talent for being in the right place at the right time. So yes, savor the alignments. They gave us data we might never see again. But let them guide testable predictions, not teleology. The sky did not schedule a performance for us. It kept its own time. We just happened finally to look up when the curtain rose. When 3IATLAS swept past Mars's orbital neighborhood, it briefly turned the red planet into a front-row seat for one of the rarest spectacles in astronomy, a visitor from another star. On Earth, telescopes could only glimpse the object through the interference of our atmosphere. But orbiters circling Mars had what scientists call a clean line of sight. No clouds, no twilight horizon, no distortion, just cold empty space between their instruments and the interstellar intruder. The European Space Agency was quick to mobilize. 2 spacecraft, ExoMars Trace Gas Orbiter TGO and Mars Express, were ideally placed to observe the comet's passage. Both missions were never designed for this purpose, yet they carried spectrometers of exquisite sensitivity. With a few well-timed commands, they transformed from planetary surveyors into interstellar witnesses. The Trace Gas Orbiter, launched in 2016 to study Mars's thin atmosphere, carries a pair of high-resolution infrared instruments, Nomad Nadir and Occultation for Mars Discovery, and ACS Atmospheric Chemistry Suite. Normally, these instruments sniff out methane water vapor and trace gases hovering above Martian plains. But during the narrow window of Atlas's approach just a few million kilometers from Mars's orbit, they were reprogrammed to look outward. Their job was simple but delicate: to search for spectral fingerprints of known cometary volatiles in the near and mid-infrared and to measure their ratios. From Mars's position, Atlas presented a geometry impossible from Earth. The comet's coma faced a slightly different phase angle, allowing the instruments to see how sunlight scattered through its gases from a side perspective. That geometry enriched the polarization and emission data already gathered by ground-based telescopes. Where Earth-based instruments like Keck and VLT struggled with atmospheric absorption lines, especially around CO2 bands, the TGO's orbit above the Martian atmosphere gave unfiltered access to those wavelengths. It was like moving the entire observatory above Earth's haze into the crisp vacuum of interplanetary space. The Mars Express spacecraft, older but no less resourceful, joined in. Its SPECAM and Omega spectrometers, veterans of countless atmospheric scans, were repointed toward the moving speck of light. Their purpose was twofold: first, to cross-check Atlas's reflected sunlight spectra against TGO's emission data; second, to attempt low-resolution imaging photometry that might constrain the comet's brightness variations. Mars Express, orbiting more elliptically than TGO, could adjust its observation times to catch the comet under different solar angles, providing temporal sampling complementary to the continuous Earth-based watch. For a brief period in late 2025, the 3 vantage points, Earth, Mars, and space-based assets near Earth's L1, formed a triangulated observatory spanning 200 million kilometers. The resulting geometry allowed scientists to calculate 3-dimensional jets and to isolate scattering angles responsible for the mysterious negative polarization. It also gave a chance to verify whether the Sunward plume really pointed against the solar wind or merely appeared that way from one line of sight. The Mars orbiter's data filled in the blind spots of terrestrial telescopes. Earth-based instruments are bound by our atmosphere's opacity. Many key gases like CO2CO and some metal carbonyls absorb strongly at infrared wavelengths between 2 and 5 microns, precisely where their diagnostic features lie. From Mars, TGO's ACS Mir module could view those regions freely. Analysts later reported a suite of faint but consistent emission lines near 7 microns consistent with carbon monoxide excited by solar UV, supporting the hypothesis that the comet's environment was rich in CO gas. No single spectral line proved the existence of NiCO 4, but the absence of iron lines and the persistence of nickel emissions were confirmed independently, lending credibility to ground-based detections. Beyond chemistry, the Mars Vantage offered dynamical insight. As the comet passed near Mars's orbit, small shifts in its apparent motion, relative to background stars allowed the orbiters to measure its non-gravitational accelerations with extraordinary precision. These accelerations, driven by uneven outgassing, helped refine the trajectory and predict where the comet's tail structures should appear. The results confirmed the Sunward jet wasn't a numerical artifact. Even from Mars's position, the same offset was visible, although slightly reduced evidence that projection effects alone could not fully explain it. For mission engineers, the operation was a logistical ballet. The orbiters had to synchronize attitude control and instrument calibration while maintaining Mars-facing operations. Commands were uploaded days in advance based on predicted ephemerids, shared by NASA's JPL Horizons and ESA's Flight Dynamics team. Every minute counted. A delay of an hour could mean the comet slipping beyond the narrow instrument field. During the critical week of observation, teams in Madrid, Darmstadt and Moscow worked around the clock, coordinating with terrestrial observers in Hawaii and Chile via late-night Zoom calls, a modern echo of the same global coordination once reserved for eclipses. When the data finally returned, they carried both confirmation and confusion. Confirmation because TGO and Mars Express verified the presence of a volatile-rich coma dense in CO2 and CO. Confusion because their models of solar-induced activity predicted a far weaker brightness given the comet's distance and albedo. Something about Atlas's dust or gas coupling was more efficient than expected, possibly hinting at porous grains or metal-enriched microsurfaces that trapped heat differently. The results didn't resolve the mystery, they complicated it, elegantly adding new parameters to the equation instead of solving it outright. Perhaps the most subtle contribution from Mars was temporal. Its instruments caught Atlas a few days earlier in its heating curve than Earth could. That difference let scientists see the onset of activity when the first jets lit up and nickel lines emerged. For the first time, we watched the chemical engine ignite, not just burn. The timing sequence stitched together from Mars, Earth and space observatories painted a cinematic view, a distant speck warming under sunlight, exhaling carbon monoxide and nickel vapor as it crossed the orbit of a red planet watched by robotic eyes. In retrospect, those ESA campaigns marked a quiet turning point. They demonstrated that planetary orbiters could double as deep space observatories, giving humanity multiple viewpoints within one solar system, an accidental interplanetary telescope array. They also showed that collaboration, not coincidence, is what turns geometry into science. Without those extra eyes above, Mars 3IATLAS would have remained a flatter story, still fascinating but missing depth. From its lonely track, the comet may never have known it was being watched from two worlds, yet its passage bound those worlds in shared purpose: one species, two planets, one mystery, and a bridge of light between them. When 3IATLAS first blinked into our telescopes, it felt like a cosmic accident, a single whisper caught in the noise. But the age of accidents is ending. The next interstellar visitor will not slip quietly through a handful of CCD frames. It will be greeted by algorithms that never sleep, telescopes that sweep the entire sky every few nights, and scientists who've learned that what seems improbable today is simply what hasn't yet been automated. At the heart of this transformation stands the Vera C. Rubin Observatory, perched on Cerro Pachon in Chile, its 8.4-meter mirror polished to within nanometers and paired with the largest digital camera ever built, 3.2 gigapixels wide. Beginning full operations later this decade, Rubin will scan the southern sky in a rhythmic heartbeat, known as the Legacy Survey of Space and Time LSST. Every clear night, it will image tens of thousands of square degrees, returning to the same patches every few days. The result, a dynamic atlas of the heavens' motion, brightness and change logged with machine precision. Under that cadence, nothing transient can hide for long. The faint, fast streaks of near-Earth asteroids, the distant pulses of supernovae, even the subtle drifts of interstellar bodies will all stand out against the background of eternity. For each exposure, Rubin's automated pipeline will extract moving objects in real time, feeding them into AI classifiers trained on millions of synthetic orbits. Within minutes, an algorithm will recognize that a newly found dot is moving too fast, its path bending too little to belong to the Sun's gravitational family. A hyperbolic signature, the fingerprint of an interstellar origin, will trigger alerts distributed worldwide. Where it once took weeks to confirm Oumuamua's nature, the next 3I-class object might be flagged before breakfast. Observatories across the globe will receive machine-readable coordinates and spin up their instruments, automatically radio dishes tuning to molecular lines, infrared arrays, ready to measure thermal flux, and small robotic scopes positioning for photometry. Even spacecraft like ESA's Comet interceptor waiting at the L2 point may be pre-programmed to pivot toward promising targets. The result will be a kind of interstellar meteorology, a discipline as empirical and continuous as weather forecasting but focused on visitors from other suns. Instead of rare events, we'll see patterns, distributions of composition, albedo, and density that map how different star systems manufacture and eject their debris. Scientists will talk of C-type interstellar comets, metal-rich hyperboloids, or CO2-dominant bodies, much as meteorologists classify clouds or storms. Each discovery will refine statistical models of planetary system evolution, hinting at which stars are prone to violent scattering, which nurture volatile-rich worlds, which forge metals deep enough to cast off nickel breath like Atlas. To sustain this flow, Rubin's database will act as an early warning radar for the solar system. Its AI modules will rank candidates not only by trajectory, but by weirdness objects with unusual light curves. Color indices or motion residuals will be elevated for human review. Over time, the system will learn from its own false alarms, becoming an autodidactic astronomer, its neural networks refining intuition faster than any individual could. In this partnership, human curiosity becomes the feedback loop, scientists validating, labeling, and feeding the machine better truths until the machine begins returning better questions. By the late 2020s, it's plausible we'll detect dozens of interstellar objects each year. Some will be dusty comets like Borisov, some metallic shards like fragments of Atlas, others small meteoroids that flare briefly upon hitting Earth's atmosphere. Already seismometers and global fireball networks have flagged possible interstellar meteors, their hyperbolic speeds betraying origins beyond the Sun. The difference now is infrastructure, an array of instruments linked by code, cross-referencing sky surveys, radar pings, and all-sky cameras in real time. The dream is to catch one early enough for interception, a fly through a sample, a microscopic touch of alien dust. And with that capability comes a subtle cultural shift. For centuries, astronomy has been about permanent stars that barely move, galaxies that change over eons. The Rubin era flips that script. The night sky becomes a streaming service of phenomena refreshed every 72 hours, each transient a message from deep time. Our databases will fill with light curves and spectra that no human eye has ever seen directly. Students will scroll through the feed of the cosmos like meteorologists reading weather maps, forecasting which patch of sky will next light up with a wanderer's glow. It's a future both thrilling and humbling. Thrilling because for the first time we'll treat interstellar visitors not as miracles, but as data sets, dozens, then hundreds, then thousands, each with its own orbit and chemistry. Humbling because the deluge will remind us how little of the galaxy we've actually sampled so far. Atlas, for all its strangeness, may be a common species, a routine product of some galactic process we've just begun to glimpse. The shift will also blur the line between discovery and understanding. AI will notice anomalies long before we can interpret them, forcing us to become philosophers of our own machines, curators of curiosity. What patterns will emerge when neural nets, not human eyes, decide what's worth following? Will they too develop their own hierarchy of awe, objects that don't fit chemical signatures that whisper of processes unmodeled? Perhaps someday the first truly alien artifact will be spotted not by an astronomer at all, but by an algorithm quietly comparing light curves at 3 a.m., flagging something it cannot classify. And yet, for all the automation, the heart of the work remains human. The wonder, the sleepless nights, the choice to look up instead of away that cannot be programmed. Rubin's great gift is not just data, but tempo. It will make the cosmos move at human speed fast enough for our lifetimes to intersect its surprises. We will no longer wait centuries between revelations. The next Atlas could appear any month, any week, and our networks will be ready. Imagine the alert feed on some future morning object 9I2269A discovered, hyperbolic velocity confirmed, spectra pending, and somewhere someone will feel the same jolt of wonder that astronomers felt with Oumuamua, Borisov, and Atlas, the recognition that a new messenger has entered the solar system, bringing with it another lesson in humility and possibility. Except this time, the message will not vanish into the noise. This time we'll be listening. What finally would it take? What piece of evidence would push 3IATLAS or any future visitor across the invisible line between weird and engineered? The question hovers at the edge of every late-night discussion whispered between data plots and coffee cups. Because unusual is not enough. The universe is prodigious in its creativity. It carves hexagonal storms on Saturn and builds self-organizing dunes on Titan. Nature is an artist of symmetry and surprise. To accuse it of invention requires more than astonishment. It requires pattern with purpose. Start with the most basic benchmark resolve structure. If future imagery, say, from a Mars orbiter, or eventually a purpose-built interceptor, were to show bilateral or radial symmetry that matched no known geological process, the conversation would change overnight. Nature can form smooth spheroids, jagged shards, or layered strata, but it rarely forms exact regularity. A hexagon on Saturn is a wave pattern. A repeating lattice in metal implies machining. If a future interstellar object revealed precise angles, repeating panels, or aligned apertures features with uniform pitch and reflection, the argument would leave chemistry behind and enter engineering. Second, albedo patterns. Real comets are patchworks of dirty snow, their reflectivity dictated by chance and chaos. But a surface with high contrast grid-like reflectance, bright and dark regions repeating in ratios or orientation would imply control. Analysts already model how light curves change as irregular bodies tumble. From these they can reconstruct crude shapes. A periodic light modulation that remains stable over many rotations with amplitudes too consistent for a rubble pile would hint at deliberate balance. Even more compelling would be a non-random spin evolution, if the rotation period changed in discrete steps near perihelion, as if reacting to heating in a controlled way, rather than gradually it would raise eyebrows from cautious to electric. Third, spectral narrowness. Nature's emissions sprawl. Thermal lines broaden with temperature, molecular bands blend into families. But industrial materials, especially alloys doped semiconductors, or specific oxides produce narrow band features that align with laboratory spectra. For example, a glint around 0.84 microns consistent with anodized aluminum, or a sharp feature near 10 microns from titanium oxides used in high-temperature ceramics. Such signals, if isolated and persistent, would be unlike any comet dust measured so far. Even more damning would be emissions that change with solar angle, as though reflecting from adjustable surfaces. Random regoliths don't tune their brightness by geometry. Fourth, electromagnetic coherence. Natural radio emissions are broadband noise hiss static bursts. A signal with narrow spectral width repeating modulation, or Doppler drifts consistent with deliberate beam steering would be transformative. The SETI community has protocols for this verify frequency stability rule at local interference triangulate. So far, every narrowband detection has dissolved under scrutiny. But if an interstellar object produced such coherence in synchrony with its rotation, or displayed a repeating pulse train unrelated to its orbital dynamics, the term technosignature would shift from speculation to taxonomy. Then there is thermal behavior. Nature absorbs sunlight and re-radiates it smoothly, according to the Stefan Boltzmann law. An engineered body might display selective emissivity, heating unevenly, or cooling more slowly than physics allows. Infrared light curves from an approaching object could reveal this areas that stay cooler than expected under direct illumination, or warmer long after sunset, implying insulation or active temperature control. A comet can lag, a machine can regulate. Even more persuasive would be maneuver-like motion. Not the slight chaotic acceleration of outgassing, but a sustained vector-consistent deviation from gravity thrust, without exhaust repeated on schedule. Oumuamua's gentle push inspired speculation, but its directionality fits sunlight-driven sublimation. A genuine anomaly would repeat predictably or scale linearly with solar flux like a sail adjusting to wind rather than a random vent spewing gas. Nature can shove, intention steers. Each of these signatures has a natural analogue, a way for skepticism to breathe. Symmetry could arise from fracture planes. Albedo contrast could come from uneven ice crusts. Narrow lines could belong to minerals we haven't catalogued. That is why science demands convergence, several independent impossibilities aligning on the same object. No single measurement will ever convict the cosmos of engineering. But a pattern geometry, modulation chemistry, and dynamics all conspiring toward coherence would shift the burden of proof. It's useful to remember how Earth itself would appear if glimpsed from afar. A visitor from another star watching our planet transit the Sun might note an atmosphere laced with oxygen and methane in disequilibrium radio burst clustered near the 21-centimeter hydrogen line, night-side illumination modulated by rotation. Those are statistical signatures of civilization, not portraits of cities. The same logic applies here. Proof will arrive statistically first anomalies that rhyme too often long before we ever photograph a rivet. And yet there's a subtler philosophical threshold, meaningful pattern versus purposeful design. Weird is when data defy current models. Designed is when data conform to a different intelligible order, one that implies constraint, feedback, or goal. The former challenges our chemistry, the latter challenges our anthropology. We must ask, not only is it possible, but is it simpler? In science, the simplest model that explains the data wins. To claim engineering, we must show that physics alone requires more assumptions than intent. Therein lies the paradox of discovery. To prove an artifact, you must first eliminate every miracle of nature, then accept one of mind. The bar is high, and rightly so, because once crossed, it cannot be uncrossed. If that moment ever comes, if some future telescope catches a visitor whose surfaces align in perfect symmetry, whose reflections pulse like a heartbeat, whose chemistry matches nothing. In the periodic patience of nature, the world will not need a press release. The images will speak the universal language of geometry. Until then, the only thing engineered with certainty is our capacity for wonder, the restless human need to separate pattern from chaos, signal from noise, artifact from awe. Even if 3IATLAS turns out to be nothing more than a comet, a natural unthinking child of physics, it would still rewrite the story of how worlds are born. Because nature, when it misbehaves, this profoundly forces us to redraw the boundaries of the possible. The most conservative outcome is in truth a quiet revolution in planetary science. If the nickel-carbonyl emissions, the CO2-rich chemistry, and the strange polarization all prove natural, then our models of planet-forming disks must change. Today's textbooks describe young solar systems as layered pancakes of gas and dust arranged by temperature-refractory metals near the star water and carbon dioxide further out methane and nitrogen at the rim. Heavy elements condense together, ices freeze in neat rings, and the boundaries between them, the snowlines, define what kind of worlds emerge. But Atlas challenges that geometry. Its mixture of high metal content and carbon dioxide ice implies a hybrid nursery one where metals and volatiles intermingled in ways we have not seen before. To build a body like Atlas, a protoplanetary disk would need zones of overlapping chemistry pockets where CO2 could freeze while nickel grains stayed mobile. That suggests far more complex temperature gradients, perhaps sculpted by magnetic turbulence or episodic flares from the young star. A single interstellar visitor thus becomes a window into the thermodynamics of a sun long extinguished. The nickel without iron problem would also upend our understanding of metal partitioning. In every known system, nickel and iron travel together, forged side by side in supernovae and condensed into meteorites in a near-constant ratio. If Atlas really exhaled nickel but not iron, then nature must have a mechanism to separate sibling elements, a galactic centrifuge we've never modelled. Perhaps in some cold carbon-rich disks, carbon monoxide binds preferentially to nickel atoms, dragging them into the volatile phase, while iron remains locked in silicates. Or perhaps charged grains near magnetic fields sort themselves by atomic weight. Either way, the chemistry implies a metal refinement process built into the galaxy itself long before any civilization existed to imitate it. The lesson would be humbling. What we call industrial chemistry might be cosmic chemistry happening unobserved for billions of years in every nebula. Then there's the volatile hierarchy. Our own comets from Halley to Rosetta's 67P are mostly water with a dash of CO2. Atlas reverses the recipe. That inversion means that in many planetary systems, water may not be the universal solvent of life, merely one among several frozen currencies. If carbon dioxide dominates, it redefines what counts as habitable. Worlds forming in CO2-rich regions could evolve with thick, choking atmospheres, their oceans replaced by supercritical carbon tides. For astrochemistry, this would demand a new grammar planetary evolution, written not just in H2O but in CO2, CH4, NH3, and exotic ices we have barely catalogued. Even the boundaries of the habitable zone, those delicate rings we map around stars, would need to shift. Life, or at least complex chemistry, might thrive under colder suns than we once imagined. Optically, the extreme negative polarization tells another story. To produce such deep and narrow light scattering, Atlas's surface grains must be unusually porous, fractal, or metallic. That implies a dust formation pathway different from the compact aggregates of our own comets. Models would need to accommodate fluffy, electrostatically bonded grains, perhaps built in low-density regions of protostellar disks or ejected from giant impacts. Those structures could explain why Atlas's light behaved as if reflected from metal. The voids between grains created microcavities that scattered light coherently. It's an insight not just for comets, but for every field that studies cosmic dust, from exoplanet atmospheres to the opacity of galaxies. If confirmed, these findings would ripple outward through astrochemistry, metallurgy, and cosmochemistry. The notion that simple comets encode information about their parent star's metallicity would become a guiding principle. Researchers could use interstellar objects as portable core samples of alien disks. Instead of waiting for distant telescopes to resolve tiny protoplanetary rings, we could let the fragments come to us, each one a messenger carrying isotopic ratios, grain morphologies, and volatile fingerprints from across the Milky Way. A discipline now in its infancy, interstellar planetology, would mature overnight. Even the presence of Nisio 4, if purely natural, would be historic. It would mean that carbonyl chemistry occurs spontaneously in space, under mild heat, and vacuum bridging inorganic and organic synthesis. Carbonyl complexes are the stepping stones toward catalytic reactions. They help carbon chains reorganize metals, change oxidation states, and complex organics form. If such processes are common on comets, then the chemical seeds of metalloproteins, enzymes, and catalysts could scatter through galaxies like pollen. The boundary between geochemistry and biochemistry would blur further. In that sense, proving Atlas natural would bring us closer to understanding life's ubiquity, not farther. Textbooks would have to expand their diagrams. The neat concentric zones of rock ice and gas would give way to gradients, feedback loops, and exceptions. Terms like snowline or frost front might evolve into plural ice lines, each tuned to a different molecule and magnetic context. Planet formation models would include chemical weathering in the nebula, not just accretion of solids. And nickel, once a minor trace element in cosmochemistry, would graduate to a key diagnostic for disk evolution. All of this without a single alien machine. Just chemistry, sunlight, and time. Yet that is what makes science beautiful, the revelation that even without intention, the universe behaves as though it were experimenting. Each new anomaly refines the grand experiment's variables. A natural atlas would tell us that nature itself is more inventive than we ever credited, capable of producing effects so intricate that they mimic design. It would reaffirm a quiet truth: every mystery when solved doesn't close the door to wonder, it opens it wider. And so if Atlas proves natural, it will still have changed everything. Our catalogues, our equations, our metaphors. It will remind us that progress in science doesn't require visitors from the stars, only the humility to see the alien within the ordinary. If after every cautious test, every control, every null hypothesis, 3IATLAS was shown to be engineered, the revelation would not unfold with fanfare, but with an almost unbearable quiet. There would be no single gasp, no broadcast announcement, only graph spectra and light curves that refused to yield to natural explanation until the only model left standing carried intent. And then the true questions would begin, not of origin, but of meaning. Let's imagine this carefully, without hysteria, without tabloids, just as a thought experiment in proportion. Suppose the evidence was decisive: a geometric lattice resolved on the surface, a repeating spectral modulation timed with its rotation, a thermal pattern indicating controlled emissivity details so coherent that no geological process could mimic them. The object is confirmed interstellar, moving freely with no sign of active propulsion. Its materials, perhaps nickel-based alloys doped with carbonyl residues, are consistent with industrial chemistry yet degraded by cosmic erosion. That scenario, an ancient autonomous machine adrift, fits what mathematician John von Neumann once envisioned: self-replicating probes launched by long-gone civilizations, each designed to explore and multiply across the stars. The logic behind such machines is simple and chillingly efficient. A single civilization capable of building a probe that can harvest raw materials and build copies of itself could fill a galaxy in 10 million years, an instant on cosmic timescales. If even one ancient culture chose expansion, their devices could now be everywhere, dormant or decayed, blending with asteroids and comets. Some might serve as observation nodes, silent data gatherers. Others could be industrial remnants, relics of a civilization that mined and refined metals on a scale we struggle to imagine. Perhaps 3IATLAS was one such relic, a derelict factory ship or fragment of a refining process, its nickel-carbonyl emissions not intentional signals, but chemical ghosts of its operation. That idea, astonishing though it is, would demand discipline, not delirium. The first rule would be containment of interpretation. The scientific method has protocols for this. The SETI post-detection framework, revised repeatedly by the International Academy of Astronautics, lays out measured steps, confirm with independent instruments, involve multidisciplinary teams, avoid premature public claims, and publish data transparently. The goal is not secrecy, but methodical sobriety to ensure that extraordinary evidence survives extraordinary scrutiny. The next rule, international stewardship. The discovery would not belong to one agency or nation. It would become humanity's shared artifact, demanding cooperation between scientists, ethicists, and diplomats. Who studies it? Who approaches it? What if retrieval alters it, contaminates it, or wakes it? These questions drift from astrophysics into philosophy. Every action, even observation, becomes a mirror test for our species' maturity. If such an object were inert, it would be studied much like a meteorite through remote sensing. Careful modelling, maybe eventual interception by a robotic probe. The priority would be context, not contact, determine its age trajectory and decay state. Its orbit might reveal its origin, perhaps from a region dense with old stars or even from intergalactic space. Isotopic dating could show whether its materials predate our Sun. Every result would cascade into new fields: archaeoastronomy, astroanthropology, xenoengineering. Entire generations of scientists would build careers on reconstructing the physics of minds we never meet. But suppose for a moment that it wasn't inert. Suppose sensors detected non-thermal modulations or self-correcting orientation, or faint electromagnetic bursts, synchronized to perihelion behaviors implying awareness, however minimal. That scenario would activate another clause in the protocols: no interference without consensus. The global community, through the UN or an emerging consortium, would debate whether to respond. SETI researchers have long discussed active SETI, the deliberate broadcasting of messages. Here, the reverse might apply: active silence, a moratorium on hailing something whose nature and thresholds we do not understand. In practical terms, science would lead cautiously. Radio telescopes would monitor for repetition. Optical arrays would map its albedo variations. Plasma instruments would measure how solar wind interacts with it. The goal would be to observe without perturbing the way one studies a sleeping giant. No spacecraft would be sent hastily. No probe would attempt to dock or sample until consensus and containment procedures existed. The motto would be, first, do no harm to it or to us. Philosophically, the discovery would rearrange everything, yet change almost nothing. Religions would adapt. Art would surge. Economies might tremble briefly and then resume. But at the individual level, the realization would be paradoxically intimate. We would learn that intelligence is not unique yet, that solitude is temporary. The alien would cease to be a speculative mirror of our fears. It would become an ancient datum in the same cosmic ledger we occupy. The most likely form of engineering we might find would not be communicative, it would be archival. Machines built to last epochs, not to converse. Their silence would be their story. Perhaps their makers are long gone, their stars cold. The object's purpose might be no more urgent than ours when we launch Voyager, to be a trace, a signature of having existed. In that case, the ethical burden shifts from contact to curation, how to honor the artifact without claiming ownership. Museums preserve the tools of extinct cultures with reverence. This would be a museum without walls, its exhibits still orbiting the sun. And what of the fear some will imagine infection, invasion, awakening? But a probe crossing interstellar space for millennia is almost certainly inert entropy's prisoner, not a predator. The wiser fear is subtler, that we might misinterpret or destroy it, before understanding its story, repeating the ancient human pattern of curiosity outrunning humility. In the long view, even proof of engineering would be less about technology than about time. A message written in machinery, not words, reminding us that intelligence is older than our species and more patient than our empires. It would confirm what many already suspect, that the universe does not waste the capacity to know itself. The challenge would be not to mythologize it, but to fold it quietly into the ongoing discipline of discovery. To treat it paradoxically as we treat any rock, any comet, any anomaly, by asking questions, testing answers, and letting the evidence lead rather than the story. The only real revolution would be one of perspective, realizing that our telescopes were never looking outward alone, they were all along part of a large network of watchers. If 3IATLAS were engineered, our proper response would not be to panic or to worship, but to listen to the data to each other, to the vastness that now feels suddenly inhabited. The discovery would not make us less human. It would invite us to become more so rational, careful, compassionate observers in a universe that at last answers back with something other than silence. In the modern world, a discovery doesn't unfold in silence, it unfolds in headlines. Before the data can even cool on the servers, the story escapes its laboratory cocoon and migrates to the public square where awe and algorithm meet. For 3IATLAS, that migration began almost instantly. A technical memo turns into a tweet becomes a blog becomes a viral video. The object itself travels through the solar system slower than the rumours about it travel across Earth. This is how narratives form now, not in observatories, but in feeds. They form in the pause between embargo and explanation. When a preprint appears on Arxiv, reporters skim the abstract sea phrases like unusual nickel abundance or Sunward jet and fill in the rest with imagination. Within hours, the headlines bloom. Astronomers detect metal vapors on interstellar object alien tech. Each retelling nudges the tone upward, a whisper sharpening into a declaration. By the time scientists correct the record, the myth has already gone orbital. Embargoes once existed to prevent this cascade. Journals coordinate with media outlets so that new findings can be verified, contextualized, and released simultaneously, allowing experts to speak before speculation metastasizes. But in the age of preprints, the embargo is porous. The moment data go public, even unreviewed someone will interpret them for clicks. It's not malice, it's momentum. Attention is the currency of the internet and ambiguity is its mint. So how can ordinary readers, people of curiosity and good faith, navigate this information storm? It begins with source awareness. Ask, where does the claim originate? If it comes from a peer-reviewed paper in Nature or the Astrophysical Journal, it has passed through the crucible of anonymous critique, its data audited by peers who specialize in skepticism. If it comes from a preprint, that means it's science in progress, valuable, timely, but provisional. Preprints are drafts released so others can test, replicate, or refute. They're not final verdicts. Next, look for instrument and replication. Every astronomical claim lives and dies by its tools. Was the anomaly seen by one telescope or many, in what wavelengths? Did independent teams on different continents observe the same signature? When Atlas's nickel emission was first reported, it was the replication by the European Southern Observatory that turned rumour into result. Science, unlike stories, strengthens not by repetition of words, but by redundancy of evidence. Then comes context. Science reporting often omits the statistical backbone of discovery. The error bars the control samples, the null results. A line in a paper might read nickel tetracarbonyl detected at 3s confidence. To specialists that means intriguing but not confirmed. To a headline it becomes nickel gas found unprecedented proof. The difference lies not in deceit but in translation. A healthy reader learns the dialect. Significance is not certainty. Correlation is not causation. Detection is not discovery. Also note who is speaking. In the early days of a finding, quotes often come from researchers peripheral to the data experts reacting in real time. Their role is to provide perspective, not confirmation. Genuine co-authors tend to sound understated, even dry. That restraint, far from dulling the story, is a hallmark of credibility. The louder the claim, the weaker the data set usually is. The most profound discoveries arrive in whispers. The press itself wrestles with a paradox to inform it must simplify, but simplification flattens nuance. A science journalist under deadline must choose between technical accuracy and narrative clarity. So they borrow metaphors, sunward jet, nickel breath, alien fingerprint phrases that spark wonder but also mislead. As readers, we can honour their intent while remembering that metaphors are bridges, not destinations. Social media adds another layer amplification without verification. A claim travels faster than the correction that follows it. The first post you read about a discovery will likely be the least accurate because it was written before the facts settled. In practice, this means that patience. The discipline of waiting 2 or 3 days for official releases becomes a new scientific skill, a civic virtue. The algorithms favour immediacy, science favours delay. Learning to live in that pause is the modern version of critical thinking. When the next alien headline flashes across your feed, try a small experiment. Don't react. Pause. Open the actual paper if it's public. Skim the methods section. Look for words like tentative possible requires further confirmation. Check if the authors themselves use cautious language. If they don't, be wary. Scientists rarely proclaim until replication has cornered doubt. Ask whether the data come from a single detection channel or a convergence of multiple ones, optical, radio, infrared. True anomalies survive cross-examination. A useful mental model: imagine a pyramid. At the base are raw detections, pixels, spectra, noise. Above that, interpretations, chemistry, motion structure. Above that, models and analogies. And at the narrow top, the peak that the media love, is speculation what it means. The wider your base, the steadier your summit. The narrower your foundation, the faster your tower of certainty collapses under scrutiny. Science builds from the bottom up. Stories tend to fall from the top down. 3IATLAS became a case study in this interplay. The early press coverage veered between breathless and dismissive. One outlet declared NASA confirms alien metal vapor, while another retorted nothing to see here. The truth has always lived in the middle, a complex, incomplete picture of chemistry that no one yet fully understood. Eventually, patient reporting caught up long-form articles, podcasts, documentaries that explained how uncertainty itself was the headline. The story matured from sensation into reflection. That maturation process is slow but necessary. The media's first job is to attract attention. The scientist's first job is to interrogate attention. Between them lies the public's job to practice discernment. In an age where anyone can publish a theory before breakfast, skepticism is not cynicism, it's compassion for the truth. It protects science from being devoured by its own wonder. So when the next interstellar object lights up the sky, remember, awe is healthy, immediacy is hazardous. Ask where the data came from, whether others have seen the same thing, and whether the results have survived peer review. If you can't find an answer yet, that's fine. Mystery takes time. The universe moves on million-year orbits. Our news cycles move in hours. The trick is to find your footing between them, to be excited without being consumed, curious without being credulous. Because in the end, science is not a race to publish. It's a conversation sustained across generations. The pause between discovery and understanding is not a void, it's the very space where truth gathers strength. If you could stand inside the moment of discovery, not the headline, not the paper, but the heartbeat of it, you'd find no fanfare. You'd find people tired, caffeinated, blinking at monitors under artificial dawns, trying to decide whether the faint wiggle on their screen is real or just another glitch. That's where 3IATLAS truly lives, not in the sky, but in those sleepless hours that scientists never film. Picture it an observatory dome in Chile or Hawaii, the air thin and cold enough to sharpen every breath. A few red lights glow above control consoles. The telescope's motor hums softly as it slews across the night, tracking a dot no wider than a pixel. Someone's wearing headphones. Another is clutching a thermos that's mostly gone. There's always one person joking to stay awake, one obsessing over calibration files, and one who hasn't spoken in an hour because the data are streaming in and every second counts. The Slack thread scrolls endlessly, time-stamped bursts of hope and anxiety. Seeing's bad 1.7 arcsec. Spectrum looks clean, no moonlight contamination. Wait, what's that spike at 4.7 microns? Hold. Could be flat field error. Checking with the pipeline. The pipeline, the automated software that turns photons into numbers, has its moods. Sometimes it's the hero catching a faint emission line that no human eye could see. Sometimes it's the villain inventing signals from bad pixels or cosmic rays. And so the night stretches between exhilaration and suspicion, every discovery followed by a second act of doubt. That doubt isn't cynicism, it's affection for reality. The astronomers who study interstellar objects know how easily nature teases. They've seen ghosts before, a satellite flare mistaken for a tail, a cosmic ray masquerading as a spectral line. They've learned that the real miracle is not seeing something strange, it's confirming that it stays strange after daylight. So they test again and again. They rotate the instrument, rerun the reduction, subtract the background differently. Each step eats minutes, hours, but that's the rhythm of truth. When a signal survives a dozen kinds of skepticism, that's when hearts start racing. Meanwhile, outside the dome, the wind picks up. Observers check the weather forecast like gamblers watching the clock. A bank of cirrus clouds can erase a night's work. Humidity rises. They scramble to close the slit to prevent dew on the mirror. Someone mutters a quiet curse in a language of habit. Someone else, ever hopeful, starts another pot of coffee. On the other side of the world, collaborators wait at their screens. Some in offices, some at kitchen tables, children asleep in the next room. Slack pings in the dark line confirmed at 3S. Independent team sees it too. No corresponding felines, just knee. You're kidding. We double-checked the wavelength calibration. There's a pause after that message, an invisible breath across continents. Everyone knows the implications, but no one says the word alien. It's taboo, almost sacred, like whistling in a cathedral. Instead, they speak in numbers, line strength, signal to noise uncertainties. The language of restraint is how scientists pray. Later in the small hours, someone jokes that if the signal disappears by morning, they'll all quit and open a cafe. They laugh because they've said it before and because they'll never quit. The joy isn't in the answer, it's in the chase. At dawn, the sky brightens, washing away the stars. They download the last files, zip them, send them off to the analysis teams. The telescope dome closes with a mechanical sigh, and the night's heroes become shadows against the glow of the monitors. Outside, birds begin to sing, a jarring reminder that the world still turns indifferent to cosmic intrigue. Weeks later, those same data will appear in a preprint plot's neat uncertainties, quantified language sanitized of emotion. No trace of the shouting, the laughter, the 3-hour argument about a calibration offset. Peer review will trim the adjectives, editors will compress the wonder into passive voice A detection was made. But behind that sentence are faces lit by monitor glow, half-eaten cookies, and a single moment when someone whispered, "I think we have something." That's science as it actually happens, fragile, human, and profoundly communal. It's not the lone genius archetype, it's a relay race of patience. Every anomaly passes through hands steady enough to doubt their own excitement. Every confirmation is born in the tension between hope and hesitation. And when weeks later the news breaks and the world asks, "Do you think it's aliens?" the people who spent those nights will smile faintly because they know what the data cost in sleeplessness and humility. They will say, "Probably not, but it's interesting." And they'll mean it in the deeper sense that in a universe as vast as ours, the act of finding anything coherent amid the noise is miracle enough. Long after 3IATLAS has faded into the cold and the papers are archived, those who watched it will remember not the nickel lines or the tail geometry, but the feeling, the surge when numbers stopped being numbers and became possibility. That's the secret heartbeat of science, the night itself. The shared wonder of being awake together beneath a moving sky, listening for the universe to whisper back. Between the bursts of discovery there is always a lull, a stretch of silence that feels endless to everyone outside the circle of analysis. The comet moves on, the telescopes shut down, the headlines fade. What remains are terabytes of raw data sitting quietly on servers in Pasadena, Darmstadt and Tokyo, waiting to be tamed. This is the quiet between data releases, and in that stillness science does its most delicate work. It is the opposite of a news cycle. In journalism, speed is virtue. In science, speed is the enemy. The process from detection to understanding is not a river, it's a delta branching into countless small investigations, spectroscopic calibration, flat field correction, instrument drift, atmospheric modelling. Each branch must be traced to its source because a single misstep can reverse an entire conclusion. A misplaced decimal in a wavelength file can turn a nickel line into iron. An uncorrected background gradient can fabricate a Sunward jet where none exists. The boundary between extraordinary and ordinary is sometimes a fraction of a percent in photon counts. So the teams move slowly, deliberately. They cross-check instrument calibration lamps taken before and after the observations, ensuring no thermal shift in the detector changed the measured lines. They compare standard stars reference targets observed the same night to rule out atmospheric artifacts. They examine how solar activity might have altered polarization through changes in interplanetary dust. Every possibility, no matter how mundane, is hunted down because experience has taught them that the cosmos rarely deceives it, is our detectors and expectations that do. From the outside, that caution can look like secrecy. Why aren't they showing the Mars images? What are they hiding? The answer is almost always error bars. Before releasing high-stakes data, teams must quantify not only what they know, but how well they know it. In the world of space missions, a data release is not a file. It's a contract with reality, a promise that the numbers have survived every known test. Breaking that promise once damages the trust that science depends on. There's also the simple matter of logistics. Deep space data don't arrive like text messages. They trickle through bandwidth-limited links, compressed, delayed, sometimes incomplete. Instruments like HiRISE or TGO's spectrometers generate more gigabytes in a night than can be downlinked in days. Those files must be unpacked, denoised, time-synced, annotated. Different institutions handle different pipelines. Then the results must converge cross-validated by independent software. Even after that, the analysis has to clear internal review boards, because reputations and entire funding streams ride on accuracy. The price of a premature release isn't embarrassment, it's confusion, wasted effort, and lost trust. For the scientists living inside that process, the waiting is its own kind of meditation. They spend months replotting the same spectra, rotating the same light curves, watching anomalies fade as calibration improves. Sometimes the excitement evaporates quietly. A line once heralded as new chemistry turns out to be a solar reflection from a detector window. The sunward jet becomes an anti-tail geometry, not defiance of physics. These corrections don't make the story less beautiful, they make it true. Every subtraction is an act of integrity. Patience in that sense is not passivity, it's precision stretched across time. Each day of waiting trims away another illusion. When the verified results finally appear, they carry the weight of that discipline. The footnotes may look dry wavelength calibration, plus 3,3 uncertainty in polarization angle plus 1.5 degree, but within them lies the difference between speculation and knowledge. There's a ritual to it. The first internal draft of a paper ends with a phrase every astronomer knows by heart. Further analysis is ongoing. It is not an evasion. It is an act of humility, a way of acknowledging that truth in science is never final, it is only current. Even after publication, someone else will re-reduce the same data with better algorithms and find new subtleties. Discovery is recursive, knowledge refines itself in loops. Meanwhile, the public wonders, what are they hiding? The scientists poring over calibration curves at 2 a.m. wonder, what are we missing? Both are driven by the same emotion, curiosity, but they move at different tempos. The public's curiosity is instantaneous. Science's is patient. They are not enemies, they are partners bound by tension like heartbeats in different measures of the same song. And when after months the data finally emerge, processed, peer-reviewed, the errors tamed, the quiet pays off. The release notes are modest. No evidence for artificial structure. Nickel emission confirmed. CO2-H2O ratio updated. A few paragraphs that took half a year of care. The headlines may have moved on, but the truth endures. The next generation will build on it confident that the numbers beneath their equations rest on solid ground. That's the hidden rhythm of science, wonder, measurement. Correction, pause. The pause is not the absence of discovery, it is its heartbeat. It is the moment when humanity takes a breath between questions, making sure that what we've seen is real before daring to dream what it means. If 3IATLAS has taught us anything, it is that strangeness is normal, that the universe's default state is variety. For centuries we assumed our solar system was a template one star, a few rocky worlds, an ice belt, a scattering of comets that all played by the same chemical rules. But every interstellar visitor that brushes past us erases a little more of that illusion. Oumuamua tumbled like a chip of glass. Borisov flared like a snowball in a vacuum. Atlas breathed nickel vapor and reflected light as if from a polished mirror. 3 messengers, 3 dialects of physics, and each insists that the galaxy speaks not one language, but a chorus of them. Zoom out from these solitary wanderers to the grand stage that made them a galaxy stitched together by stellar nurseries, each one a forge of different ingredients. The Milky Way is not chemically uniform. It's a patchwork of metallicities and molecular clouds. Some regions rich in heavy elements from recent supernovae brew, dense disks loaded with iron and silicates, factories for rocky planets and iron cores. Others, older and more pristine, swirl with carbon and oxygen, but little metal producing icy worlds crusted in CO2 and methane. Between them lie hybrid zones where nickel and carbon share the same breath, where Atlas-like chemistry could blossom naturally. If we could line up 1,000 comets from 1,000 suns, they'd form a rainbow of compositions, not a parade of clones. This isn't speculation. It's already visible in our instruments. Radio telescopes pick up a zoo of molecules in interstellar clouds, formaldehyde, methanol, glycolaldehyde, even amino acids, each tracing different birth conditions. When those clouds collapse into stars, their debris disks inherit those fingerprints. A comet is simply a time capsule of its parent nebula's quirks. Every interstellar object we detect is in essence a fossil of another solar system's personality. The diversity shows up not only in chemistry but in optics and motion. Some visitors gleam bright and specular, others are dusky and red. Their albedos span orders of magnitude. Their polarization curves sketch out entirely new families of dust behavior. Some arrive spinning like flywheels, others drift like ghosts. Their trajectories hint at ancient gravitational dances worlds, flung away by migrating giants, fragments from disrupted moons, shards of collisions in alien asteroid belts. Each one that crosses our sky is an ambassador of chaos, proof that planetary evolution everywhere is as unpredictable as it is creative. Astronomers once worried that Atlas's anomalies meant our theories were breaking. The better realization is that the theories were too narrow. We built them on a sample size of one solar system, and mistook that for the universe. In truth, we are the outliers. Our mild star, our particular mix of water and rock, our balanced orbits. These may be the statistical exceptions in a galaxy that loves extremes. For every Earth-like chemistry, there may be countless Atlas-like chemistries where carbon dioxide, not water, sculpts the icy grains, where nickel acts as a catalyst instead of an afterthought. What we once called exotic may be simply elsewhere's ordinary. Think of the Milky Way as an immense ecosystem of chemistry. Some stars grow rich in silicon, others in carbon. Some seed their neighborhoods with iron dust, others with graphite snow. Over billions of years, their debris mingles each supernova, spicing the next generation of planets. The result is a galactic gradient of diversity, a continuum from water-bearing worlds to methane glaciers, from dusty red comets to metallic wanderers like Atlas. The more we look, the clearer it becomes. Uniformity is the myth. Variation is the law. This realization changes the scientific mood. The question is no longer, why is Atlas so strange, but why did we ever expect sameness? The shift is subtle, but profound. It recasts anomalies from threats into teachers. A comet with nickel breath is not an embarrassment to chemistry, it's an expansion of it. A sunward jet that defies expectation is not a violation of physics. It's a reminder that physics has more verbs than we've conjugated. Philosophically, this diversity is humbling. It means that when we point telescopes outward, we're not seeking confirmation of ourselves, we're meeting the plural forms of matter. Each visitor is a bridge between our world and countless others, proof that creation is not a single melody, but a jazz improvisation played across 100 billion stars. To catalogue them is to eavesdrop on the galaxy's creative process, how it experiments, recycles, mutates. Every interstellar object is both artifact and accident, a spark thrown from the grindstone of evolution. Practically, it means the next decade will look less like isolated discoveries and more like taxonomy. Rubin JWST and future missions will catch so many wanderers that we'll start classifying them the way biologists classify life. There will be families defined by volatile ratios, by reflectance spectra, by polarization behavior. We'll talk about type Ni carbonyl comets, CO2-dominant hyperboloids, tumbler fragments and mirror grains. Atlas will no longer be the outlier. It will be the prototype of a category we didn't know existed. And in that reclassification lies a quiet redemption for human curiosity. We spend centuries building models only to have the universe remind us that it was never obliged to follow them. But that's the beauty of science. Every broken rule enlarges the map. Atlas's strangeness, far from isolating it, connects it to a grander truth that diversity is the rule of cosmic design. In the deep archive of interstellar debris, sameness would be the real anomaly. So when the next wanderer arrives, and no one will whisper impossible, they'll whisper different and mean it as praise. The galaxy's creativity is its constant. We're only beginning to learn its dialects. Each new object will add a syllable, each anomaly a clause, until the sentence becomes clear there is no single way to build a world. That understanding is both scientific and spiritual, to realize that the cosmos does not repeat itself. It variates itself endlessly, beautifully, inevitably. 3IATLAS is just one punctuation mark in that vast grammar, a comma in a sentence still being written across the stars. It is late. The world has quieted. You step outside and feel the air, the faint coolness that settles when the noise of the day dissolves. Above you, the sky is the same one our ancestors stared into, trying to make sense of faint lights that refuse to explain themselves. Tonight, somewhere out there, 3IATLAS drifts again, dimming, receding, indifferent yet unforgettable. Whether it was comet or craft, natural or engineered, doesn't matter so much now. What matters is what it did to us, the way it reawakened our appetite for mystery. In an age that celebrates certainty, Atlas reminded us that not knowing is not failure, it's invitation. To be bewildered honestly and humbly is to stand at the doorway of understanding. You look up and the stars seem almost personal. The same minds that built cities and equations have also built telescopes quietly listening to the universe breathe. And the act of listening, of waiting for data, of doubting, of daring to wonder is its own form of prayer. Or, after all, is a discipline. It asks you to stay awake to beauty even when you don't have an answer yet. Somewhere in those telescopes, data still waits unreleased images, spectra, that may yet confirm or dissolve the mystery. Scientists will keep refining, checking, calibrating, whispering to each other in the long hours before dawn. That's how truth ripens, not in breaking news, but in the slow exhale of patience. And you listening here under this quiet sky are part of that process. Every question you carry, every spark of curiosity you refuse to extinguish, keeps the dialogue between mind and cosmos alive. Because science is not a monologue, it's a duet between the known and the unknown, between signal and silence. 3IATLAS has already added its verse. It taught us that we can hold wonder and skepticism in the same hand without breaking either. So breathe, let the night deepen around you. Imagine that small distant traveller gliding past the orbit of Jupiter, now a grain of light against the darkness. Imagine the countless others still unseen drifting toward us from other suns, each bearing its own chemistry, its own enigma, its own reminder that the universe is still inventing surprises. One day, soon, another will appear. 4I, numbers, climbing stories multiplying. And we'll gather again, scientists, dreamers, insomniacs, tilting our instruments and imaginations toward the sky, tracing the faint curve of motion, the glimmer of the unexpected. We'll whisper theories, argue gently, laugh at our mistakes, and wait for the next fragment of infinity to pass within reach. Because that is what it means to be alive in a cosmos like this, to remain curious, to let the unknown feed us instead of frighten us. To look up not for reassurance, but for participation. The mystery is not there to be conquered. It's there to keep us awake. And so, as you turn your gaze toward the stars, let gratitude settle in with the darkness. Gratitude that there is still so much we don't understand, that the universe still has secrets generous enough to visit. Whether 3IATLAS was a comet or something stranger hardly matters now. It has already done its quiet work. It reminded us that the sky is not done surprising us, and that wonder, when held gently, is the best kind of certainty we will ever have. Good night. Thank you so much for keeping me company tonight. Don't forget to subscribe so we can share many more stories together.